Hello, and welcome back to Learn When You Sleep. If you are joining us for the first time, you have found a sanctuary where science moves slowly, where curiosity drifts at its own pace, and where the questions we ask are meant not to alarm but to soothe. Tonight, we are going somewhere very specific in the universe, not to the brightest places, not to the most violent or the most spectacular. Tonight, we are going to the quiet places, the cold places. We are searching for the objects that most people have never thought about, and yet which may outnumber almost everything else we know of in the cosmos. Tonight, we are going to spend time with the mysterious brown dwarfs. That phrase alone might make you pause. Brown dwarfs. It does not sound spectacular. It does not carry the weight of words like supernova, or black hole, or galaxy. It sounds, if anything, a little unremarkable, a little plain. And perhaps that is exactly why it is the perfect thing to explore on a night like this, as you settle into your pillow, as your breathing begins to slow, and the sounds of the day grow more distant. Because brown dwarfs are, in almost every sense, the quiet survivors of the galaxy. In their unremarkableness, they are one of the most fascinating things in all of existence. Take a moment now to settle in. Notice the weight of your body wherever you are resting. Notice how the air feels against your skin. Notice the quiet that is beginning to gather at the edges of your awareness. This is the right kind of awareness for what we are about to explore, because brown dwarfs are not loud. They do not demand your attention. They simply exist, and they have been existing for a very long time, and they will continue to exist long after the loudest, brightest stars in the sky have gone dark. When you look up at the night sky on a clear evening, what you see is light. Thousands of points of it, each one a sun, each one burning at temperatures we cannot truly comprehend. The stars you see are the extroverts of the cosmos, pouring their energy outward in every direction, announcing themselves without hesitation. But the universe contains far more than what is visible to our eyes. Imagine a world that gathered enough mass to be a giant but stopped just short of the spark. For every star you can see, there may be objects nearby that you cannot see at all, not because they are too far away, but because they do not shine brightly enough to reach you. They glow, in their own quiet way, in wavelengths your eyes were not built to detect. They drift through the galaxy in their millions, perhaps in their billions, neither star nor planet, neither light nor darkness, but something in between. These are the brown dwarfs, and tonight, we are going to learn to see them with our minds, even if our eyes can never find them. The universe has a tendency to resist simple categories. We like to divide things neatly: star or planet, hot or cold, old or young, large or small. And for a while, those categories hold up well enough. Stars are things that burn through nuclear fusion, fusing hydrogen into helium at their cores. Planets are things that orbit stars, much smaller, not producing their own energy, simply receiving light from elsewhere. But then, nestled between those two categories, exists a class of objects that does not fit cleanly into either. They are the bridge between worlds. These objects occupy a threshold, a boundary region where the rules of both stars and planets apply, and yet neither applies fully. They are too massive to be a planet, but not massive enough to sustain the hydrogen fusion that defines a true star. They are the brown dwarfs, and they have been there all along, hiding in the cold dark, waiting for us to develop the tools and the curiosity to find them. Tonight, we will take our time with them. We will learn how they form, what they are made of, what their alien skies look like, and how long they will last. But more than that, we will explore what they mean not just scientifically, but falsifiable. Because brown dwarfs are not just interesting objects in the sky. They are a lesson in what it means to exist without shining, to endure without recognition, and to outlast almost anything else in the universe while being almost entirely unknown. So let your eyes close gently if they wish to. Let your thoughts grow softer. Let the image of a dark sky form in your mind, not a sky full of bright stars, but a sky that is mostly dark, with only a faint warmth here and there, barely visible, barely there at all. That is where we are going. Into the quiet, into the cold, into the long, patient dark of the brown dwarf world. Before we can truly understand what a brown dwarf is, we need to sit for a while with the idea of being between things. Not fully one thing, not fully another. Existing in a space that has no precise name, that does not belong cleanly to any established category. These are liminal objects. Brown dwarfs are the cosmos' liminal objects. They are threshold things. They are what happens when the universe builds something and then stops just short of completion. Not because something went wrong, but simply because the raw material available was not quite enough to cross the line. The line that separates planet from star. The line where nuclear fire begins. Let us think carefully about where that line is and why it matters so much. In the universe, mass is the great organizer. Almost everything about an astronomical object is determined by how much matter came together to form it. A small amount of gas and dust collapsing under gravity becomes a comet, an asteroid, or a moon. A larger amount becomes a planet, with enough gravity to pull itself into a sphere. More still, and you get a gas giant like Jupiter or Saturn, massive worlds of swirling cloud and crushing pressure. And then, at the top of the scale, enough matter collapses to form a star, and something remarkable happens. The pressure at the center of a collapsing mass of gas reaches a point where atomic nuclei are forced close enough together to fuse. Hydrogen nuclei are pressed so close together under such enormous heat and pressure that they begin to fuse into helium. This is nuclear fusion, and it is the engine of every true star. The sun at the center of our solar system maintains this fusion reaction at its core, where temperatures reach 15 million degrees Celsius. That fusion is what keeps the sun from collapsing under its own gravity, because the energy it releases pushes outward, balancing the inward pull of all that mass. The result is a stable, long-burning star, a fusion engine that has been running for about 4.5 billion years and will continue for several billion more. But what happens if the collapsing cloud of gas does not accumulate quite enough mass? What if the pressure at the core climbs high, but not quite high enough to sustain that hydrogen fusion reaction indefinitely? What if the temperature rises, but the threshold is never fully crossed? Then you get a brown dwarf, a smoldering ember in the dark. The dividing line between a brown dwarf and a true star is around 80 times the mass of Jupiter. Objects above that threshold can sustain hydrogen fusion and are considered true stars. Objects below that threshold cannot maintain that reaction. And at the lower end, between about 13 and 80 Jupiter masses, you find the brown dwarfs themselves. Massive enough to be extraordinary, not massive enough to burn. This is where another kind of fusion becomes relevant, the fusion of deuterium, a heavier form of hydrogen. Objects above this threshold can fuse deuterium for a time, which is why 13 Jupiter masses is the lower boundary of brown dwarfhood. Below that, you enter the realm of sub-brown dwarfs, and eventually the realm of planets. What emerges from this picture is a spectrum, a continuous gradient of objects, from tiny rocky worlds to gas giants to brown dwarfs to small dim stars to massive blazing giants. The universe does not draw neat lines. Brown dwarfs sit in the most interesting part of that spectrum, where the distinction between star and planet becomes ambiguous, and where the object must navigate a kind of identity it shares with nothing else entirely. The lines are things we draw, helpful for organizing our understanding, but somewhat artificial when laid over the true gradations of nature. Brown dwarfs sit in the most interesting part of that spectrum, where the distinction between star and planet becomes ambiguous, where the physics of both categories apply, and where the object must navigate a kind of identity it shares with nothing else entirely. Think of them as the universe's own creatures of the in-between. They form the way stars form, from collapsing clouds of gas. They have many of the structural features of stars, a layered interior, an atmosphere, a magnetic field. And yet they lack the one thing that defines a star in the most essential way. They do not burn with sustained nuclear fire. They do not fuse hydrogen at their cores indefinitely. They do not pour their light outward into the galaxy. They simply exist, quietly, patiently, in the dark. There is something worth sitting with in that image. An object that formed through the same grand process as a star, that carries within it the architecture of a star, that is built from the same material as a star, and yet which will spend its entire existence quietly cooling, slowly releasing the heat of its own formation, glowing faintly in wavelengths we cannot see, moving through the galaxy unnoticed by almost everything. Not failed, not lesser, simply different. Existing at the threshold, and finding in that threshold a kind of life that is entirely its own. To truly understand what a brown dwarf is, we need to understand what it almost became. And that means spending some time with the process of star formation, one of the most beautiful and most violent processes in the universe, described slowly enough that it can carry you gently into rest. The universe is not empty between the stars. Far from it. The space between stellar systems is threaded with enormous clouds of gas and dust, vast structures that can be thousands of light years across. These are called molecular clouds because within them, the gas is cooled enough to form molecules, mostly molecular hydrogen, the simplest possible molecule, two hydrogen atoms bound together. But also carbon monoxide, water ice, methane, and traces of many other compounds, all frozen into tiny dust grains or drifting as gas through the deep cold of interstellar space. These clouds are the nurseries of the galaxy. They are where stars are born. And like any nursery, they begin as quiet places, cold and dark, seemingly inert. But they are not inert. They are under tension, balanced between the outward push of the gas pressure within them and the inward pull of gravity. And this balance is fragile. When something disturbs a molecular cloud, the balance can break. The disturbance could be the shock wave from a nearby supernova, a massive star exploding and sending a ripple through the surrounding gas. It could be the gravitational influence of passing through a spiral arm of the galaxy, where matter is slightly more concentrated. Or it could be the slow, patient accumulation of small density variations over millions of years, until some region becomes dense enough to begin collapsing under its own weight. Once collapse begins, it is self-reinforcing. As gas falls inward, the density at the center increases. As density increases, gravity strengthens. As gravity strengthens, more gas falls inward. It is a runaway process, and it happens not in one smooth ball, but in a chaotic, turbulent way. The cloud does not collapse into a single object. It fragments, breaking into dozens or hundreds of smaller collapsing knots, each of which will become its own object: a star, a brown dwarf, a binary pair, a cluster. Each fragmenting knot begins to collapse independently, pulling in the gas around it into a spinning disk. As gas falls inward and the core grows denser, it heats up, because when gas is compressed, it grows warm. This is familiar in everyday experience. A bicycle pump grows warm when you compress the air inside it. At the scale of a collapsing cloud of gas, the temperatures that develop are extraordinary. The central region of each collapsing fragment, called a protostar at this stage, grows increasingly hot and dense. It begins to radiate energy, not yet from nuclear fusion, but simply from the heat generated by gravitational compression. This is called gravitational energy, or Kelvin-Helmholtz contraction, and it can power a forming star for millions of years before any fusion begins. Around this protostellar core, a disk of gas and dust forms, spinning around the central object. This is the protoplanetary disk, the birthplace of planets. The central object draws in more and more material from the surrounding cloud, growing more massive, growing hotter, growing more compressed at the core. For the protostars that will become true stars, the process continues until the core temperature reaches the threshold for hydrogen fusion, around 10 million degrees Celsius. At that point, the fusion reaction ignites, and the object transitions from protostar to true star. The outward pressure from the released energy stabilizes the collapse, and the star settles into a long, steady life on what astronomers call the main sequence. But for the objects that will become brown dwarfs, the story is slightly different. The process begins identically. The cloud fragments, a knot collapses, a protostellar core forms, a disk develops around it. But for one reason or another, not enough mass accumulates. The object grows, but it does not grow enough. The core heats, but it does not reach the sustained fusion threshold. And so, when the surrounding gas is exhausted or blown away, when the growth phase ends, what remains is an object that has all the structure of a forming star, but not the mass to become one. The core is dense and hot, but not hot enough for permanent hydrogen fusion. The object glows, but with a different kind of light, a different kind of warmth, a different kind of existence. It is a brown dwarf, and its life is just beginning. The formation process is worth thinking about slowly because it reveals something important. Brown dwarfs do not form through a different process than stars. They do not arise from some fundamentally different mechanism. They form through the same gravitational collapse, the same cloud fragmentation, the same protostellar development. They simply end up on the lighter side of the mass spectrum. They are stars that almost were. And that word almost carries a great deal of meaning if we let it. In everyday life, we tend to treat almost as a word of falling short, of disappointment, of potential unrealized. Almost made it, almost succeeded, almost enough. But in the context of brown dwarfs, almost carries no such weight. The universe does not judge. The universe does not have a preference for fusion over cooling, for brightness over dim warmth. It simply allows mass to collapse according to physical law, and whatever emerges from that process has its own validity, its own role, its own remarkable existence. A brown dwarf did not fail to become a star. It became exactly what its mass and the physics of its formation allowed it to become. And what it became, as we will discover over the course of this night, is one of the most enduring, most patient, most quietly extraordinary objects in the universe. We have talked about the threshold, the line that separates brown dwarfs from true stars. But what exactly is that threshold, and why does it exist? Why is it that adding just a little more mass to an object can mean the difference between a cold, dim, slowly cooling world and a blazing nuclear furnace that shines for billions of years? The answer lies deep inside the physics of matter under extreme conditions, and it is worth exploring slowly because it reveals something beautiful about how the universe is built. At the heart of any massive object is pressure. Gravity pulls all the mass inward toward the center, and everything inside the object is under enormous compression. The deeper you go, the more mass is pressing down from above, and the greater the pressure becomes. This is true for planets as well as stars, but the scale is very different. For a planet like Earth, the pressure at the core is enormous by human standards, millions of times atmospheric pressure. But it is not enough to affect the fundamental behavior of atoms. The atoms in Earth's core are compressed, but they retain their identity, their electrons orbiting their nuclei in much the same way as they do at the surface. For a gas giant like Jupiter, the pressure is much higher, and near the center, hydrogen is compressed into a metallic state, a dense fluid where electrons move freely rather than orbiting individual atoms. This metallic hydrogen conducts electricity and creates magnetic fields, and it is one of the more exotic forms of matter found in our solar system. But still, the atomic nuclei at Jupiter's core are not fusing. The temperatures and pressures are not yet sufficient. Now imagine continuing to add mass to Jupiter. As mass increases, gravity increases. As gravity increases, pressure increases. As pressure increases, temperature increases, because compression heats gas. The core grows hotter and denser as each additional piece of mass falls in and adds to the weight pressing down. At around 13 times the mass of Jupiter, something new happens. Deuterium, a form of hydrogen whose nucleus contains one proton and one neutron rather than just a proton, begins to fuse. Deuterium fusion ignites at lower temperatures than ordinary hydrogen fusion, and it can begin in objects of this mass. This is one reason astronomers use 13 Jupiter masses as the lower boundary for brown dwarfs. An object with at least this much mass has crossed at least one nuclear threshold. But deuterium is rare. Even in a cloud of gas with the same composition as the Sun, only a tiny fraction of the hydrogen is deuterium. About one atom in every 6,000 or so. So when a brown dwarf begins fusing deuterium, it quickly exhausts its supply. The deuterium in the core is consumed within tens of millions of years, a short time by cosmic standards, and then the fusion stops. For objects below about 80 Jupiter masses, this is essentially the end of nuclear burning. Hydrogen fusion, the sustained reaction that defines a true star, requires a core temperature of around 10 million degrees Celsius. The cores of brown dwarfs, even the most massive ones, do not quite reach or sustain those conditions for hydrogen fusion indefinitely. Why is the threshold so precise? Because the physics of fusion depends critically on the ability of positively charged protons to overcome their natural electromagnetic repulsion and come close enough together for the strong nuclear force to take over. The strong nuclear force is the force that binds protons and neutrons together inside atomic nuclei, and it is enormously powerful, but only over very short distances. For two protons to fuse, they must be brought within about a femtometer of each other, which is a millionth of a billionth of a meter. At room temperature, protons would never get that close. Their positive charges repel each other long before they could fuse. But at temperatures of millions of degrees, the protons are moving so fast that some of them can tunnel through the electromagnetic barrier by quantum mechanical effects, and fusion becomes possible. The rate of fusion increases dramatically with temperature, which is why there is a fairly sharp threshold below which sustained fusion cannot occur. So the threshold of fire, the line between brown dwarf and true star, is ultimately a quantum mechanical threshold. It is the temperature at which proton-proton fusion becomes self-sustaining, where the energy released by fusion is enough to maintain the temperature needed for more fusion. Below that threshold, the fire lights briefly and goes out. Above it, the fire sustains itself for billions of years. For a brown dwarf, the core heats up, approaches the threshold, perhaps even briefly crosses parts of it for deuterium, but never achieves the sustained hydrogen burning that would make it a true star. It is like a fire that catches briefly and then smolders, releasing heat, but not the roaring flame that would sustain itself. This smoldering is not nothing. A brown dwarf that has just formed is genuinely hot. The most massive brown dwarfs, those close to the 80 Jupiter mass limit, have surface temperatures that can reach 2,000 degrees Celsius or more, hot enough to glow a dull reddish orange, hot enough to be detectable in visible light, though faintly. But without a sustained fusion source to replenish the energy being radiated away, the cooling begins immediately. And over time, the brown dwarf grows cooler, dimmer, fainter, until it slips below the detection threshold of any instrument that observes visible light, and then below the threshold of infrared instruments as well, and then below the threshold of almost everything we currently have. The threshold of fire is crossed from below. The brown dwarf approaches, reaches toward it, just barely fails to sustain the crossing, and then begins the long, slow retreat into cold. And yet, as we will discover, that retreat takes so long, proceeds so slowly, that by the time it is complete, the universe will be almost unimaginably different from what it is today. There is a phrase that astronomers sometimes use for brown dwarfs, a phrase that is evocative and memorable, though perhaps a little unfair. They are called failed stars. And there is a sense in which that label captures something real about them, the sense that they came close to stellar ignition but did not make it. But there is also a sense in which that label misses everything important about what brown dwarfs actually are. Tonight, let us spend some time with both sides of that idea, with the physics of why the ignition does not fully take hold, and with the philosophy of why failure might not be the right word at all. When a protostellar core is forming and contracting, it is heating up through that process of gravitational compression we discussed. The core temperature climbs, and the object grows denser. If the mass is sufficient, the temperature at the core will reach the ignition point for hydrogen fusion, and the fire will catch. The object becomes a star, and the energy released by fusion halts the contraction, establishing the balance between gravity and radiation pressure that defines a stable stellar life. But in a forming brown dwarf, the mass is not sufficient. The core heats up, the temperature climbs, deuterium fusion may briefly occur, and for a time the object is hot enough and luminous enough to look very similar to a young, very low-mass star. Young brown dwarfs in star-forming regions are difficult to distinguish from very low-mass stars precisely because they are still warm from formation, still radiating the heat of their gravitational collapse. The distinction only becomes clear over time. As the surrounding gas and dust clears and the object ages, a true star maintains its luminosity through continued fusion. A brown dwarf, lacking that fuel source, begins to cool and dim. Over millions of years, the difference becomes apparent. The star stabilizes. The brown dwarf fades. Inside the brown dwarf, the core situation is governed by a physical principle called electron degeneracy pressure. This is a quantum mechanical effect that becomes important at the high densities found inside brown dwarfs and white dwarfs. As matter is compressed to very high densities, electrons resist further compression not because of thermal pressure, but because of a fundamental quantum rule. No two electrons can occupy the same quantum state at the same time. This Pauli exclusion principle, as it is called, creates a pressure that resists compression even at very low temperatures. In a brown dwarf, this degeneracy pressure eventually halts the gravitational contraction. The object reaches a stable configuration where gravity is balanced by electron degeneracy pressure rather than by the thermal pressure of fusion reactions. This is a fundamentally different kind of stability than what supports a true star. A star is held up by the ongoing pressure of its burning core, replenished continuously by fusion energy. A brown dwarf is held up by quantum mechanics, by the reluctance of electrons to be squeezed into the same space. It is a colder, quieter kind of support. Less dramatic, but no less real. The result is that a brown dwarf settles into a configuration roughly similar in size to Jupiter, regardless of its mass. More massive brown dwarfs are not much larger than less massive ones, because the increased gravity compresses the material more. A brown dwarf near the stellar threshold might be only slightly larger than Jupiter in radius, even though it contains 80 times Jupiter's mass. All that extra mass is packed into roughly the same volume, held in place by quantum mechanical forces. Inside this compact, dense object, heat is slowly conducted outward from the warm interior toward the cooler surface and then radiated away into space. Without a fusion source to replenish it, this heat represents a finite reservoir of energy, the thermal energy accumulated during formation, slowly dissipating over time. The rate at which this happens depends on the brown dwarf's mass and composition, but always it is slow. Extraordinarily slow. A brown dwarf cools by perhaps a few hundred degrees over hundreds of millions of years. The process is so gradual that on human timescales it is essentially imperceptible. Astronomers can tell that cooling is happening by comparing brown dwarfs of different ages and finding that older ones are dimmer and cooler than younger ones. But watching a single brown dwarf cool over a human lifetime would be like watching a glacier move. There is change happening, but you would need instruments far more sensitive than your eyes to detect it from year to year. So the ignition that did not sustain. The fire that caught briefly on deuterium and then faded. The core that reached toward the hydrogen fusion threshold but could not maintain the crossing. What remains after all of this is something remarkable. An object roughly the size of Jupiter, packed with the mass of dozens of Jupiters. Dense, compact, magnetic, atmospheric, layered, warm at its heart, cooler toward its surface, and radiating its birth heat slowly into the surrounding dark. Is this failure? The word failure implies a standard against which something has been measured and found wanting. It implies a goal that was not achieved, a potential that was not realized. But the universe does not set goals for its objects. There is no standard against which a brown dwarf is measured and found wanting. There is no cosmic judge who looks at the outcome of a cloud collapse and marks it as insufficient. A brown dwarf is what it is. It formed according to physical law. It occupies a stable configuration supported by quantum mechanics. It has an atmosphere, weather, magnetic fields, possibly moons. It will exist for longer than the current age of the universe several times over. It will outlast every true star that is burning tonight. Failed seems like the wrong word. Perhaps a better frame is this. A brown dwarf is a stellar object that discovered a different kind of life. Not the brief, brilliant burning of a massive star, not even the long, steady burning of something like our sun, but a different path entirely. A slower, darker, quieter, enormously more patient path. One that does not make headlines, does not illuminate nearby planets, does not scatter its material across the galaxy in a dramatic supernova. It simply exists, glowing faintly in the infrared, cooling by imperceptible degrees over trillions of years, patient beyond any measure we have a word for. There is something in that image that is worth carrying into sleep. The idea that a thing can be what it is without needing to be something else to be valuable. That existing quietly and enduring patiently is its own kind of meaning, even in a universe that tends to reward the loudest and the brightest with the most attention. The brown dwarf does not need to be a star. It is fully itself, at the threshold, in the quiet dark, cooling slowly toward a future so distant it cannot even be imagined yet. We have spent some time at the threshold of fire, standing at the boundary between brown dwarfs and true stars, looking at the physics of why some objects cross it and others do not. And we have thought about what it means for an object to approach that boundary, to feel the heat building within its core, to have all the structure and all the ingredients of a star, and yet to remain just beneath the line where sustained hydrogen burning begins. But the story of nuclear fire inside a brown dwarf is not entirely empty. There is a moment, early in a brown dwarf's life, when a brief and quiet flame does exist. Not the roaring, sustained fusion of a true star. Not the hydrogen burning that will keep our sun shining for another 5 billion years. But a smaller, softer, shorter-lived reaction, one that catches for a time and then fades, like an ember briefly glowing in a cooling hearth before the last warmth drains away. This is the burning of deuterium, and it is one of the most quietly beautiful episodes in the life of a brown dwarf. Deuterium is a form of hydrogen. Ordinary hydrogen, the most abundant element in the universe, consists of a single proton as its nucleus, with a single electron orbiting around it. Deuterium has one proton and one neutron in its nucleus, making it heavier, more stable in some ways, and critically, easier to fuse. The nuclear reaction that fuses two deuterium nuclei, or that fuses deuterium with an ordinary proton, requires a lower temperature and lower pressure than the proton-proton chain that sustains our sun. This means it can ignite in objects that never achieve the full conditions for hydrogen fusion. In any cloud of gas with a composition similar to the sun, roughly one hydrogen atom in every 6,000 is actually deuterium rather than ordinary hydrogen. That sounds like a tiny fraction, and it is. But when you are talking about an object with tens of Jupiter masses of gas, even 1 in 6,000 adds up to a meaningful quantity. A brown dwarf forming from such a cloud will have a small, but real supply of deuterium distributed throughout its bulk. As the forming brown dwarf contracts and its core heats up, it reaches deuterium burning temperatures before it reaches the threshold for ordinary hydrogen fusion. The core temperature climbs to somewhere around 1 million degrees Celsius, still far below the 10 million degrees needed for proton-proton fusion, but sufficient for deuterium reactions to begin. And when they begin, the brown dwarf briefly becomes something closer to a true star than it will ever be again. During this deuterium burning phase, the object is genuinely luminous. It radiates energy from its fusion reactions. It may even undergo a kind of mild convection in its interior, where the heat generated at the core is carried outward by rising columns of hot gas and descending columns of cooler gas, mixing the material inside the brown dwarf and bringing fresh deuterium down toward the hot core. This convective mixing means the brown dwarf does not simply burn the deuterium in its center first and then stop. Instead, it stirs itself, drawing fuel from throughout its bulk into the burning zone. The timescale for this deuterium burning phase varies with mass. More massive brown dwarfs, those close to the stellar threshold of 80 Jupiter masses, may burn their deuterium over tens of millions of years. Less massive ones, those near the lower boundary of brown dwarfhood, may exhaust their supply in just a few million years. In either case, on cosmic scales, this is a very short episode. Our sun has been burning hydrogen for 4.5 billion years and has billions more to go. A brown dwarf's deuterium flame lasts millions of years, not billions, and when it goes out it leaves behind an object that has no ongoing nuclear source of energy at all. The extinction of the deuterium flame is not dramatic. There is no explosion, no flash of light, no sudden change that would be visible from a distance. The supply of deuterium simply dwindles, the fusion reactions become less frequent, the energy output decreases, and gradually, over time, the glow fades. The object transitions from something that is generating heat through nuclear reactions to something that is simply releasing the stored heat of its formation, the gravitational energy that was deposited when all that gas fell together under gravity. From this point forward, the brown dwarf's life is one of pure cooling. Pure, slow, patient dissipation of heat into the surrounding dark. It is worth dwelling on the image of that brief flame. In a life that will extend for trillions of years, the deuterium burning phase is a moment, a flash, an episode so brief in proportion to the whole that it is almost impossible to hold in perspective. Imagine a human life of 80 years and try to represent that on a timeline extending back 10,000 years to the earliest human civilizations. Your entire life would occupy less than the width of a pencil line. The deuterium flame in a brown dwarf's trillion-year existence is something like that. And yet it is real. It happens. For those millions of years, the brown dwarf is genuinely burning, genuinely generating nuclear energy, genuinely doing something that, from certain angles, looks like the early life of a very low-mass star. Young brown dwarfs in star-forming regions can be so similar in appearance to very young, very low-mass stars that astronomers spent years developing techniques to tell them apart. Only the passage of time reveals the difference. The true star maintains its luminosity, while the brown dwarf slowly fades as its deuterium burns out and its stored heat begins to dissipate. There is a class of objects at the very boundary of brown dwarfhood, those between roughly 65 and 80 Jupiter masses, where the situation is particularly interesting. These objects can actually sustain a low level of hydrogen fusion, not the full proton-proton chain, but a related reaction called the proton-proton chain's first step involving lithium and beryllium. Some of these borderline objects may flicker between the categories over their lifetimes, briefly sustaining hydrogen reactions when their cores are hottest, then losing that capacity as they cool. They are the most ambiguous objects in this already ambiguous population, neither fully stellar nor fully substellar, oscillating across the threshold in a way that resists any simple classification. The fate of the lithium inside a brown dwarf is actually one of the tests astronomers use to determine whether a given object is truly substellar. True stars, even very low-mass ones, are hot enough at their cores to destroy lithium through nuclear reactions. A genuine main-sequence star will burn through its lithium supply within the first billion years or so of its life. But a brown dwarf, whose core never reaches the temperatures needed for lithium fusion, retains its lithium indefinitely. If you observe the spectrum of a cool, dim object and find the characteristic absorption lines of lithium, that is strong evidence that you are looking at a brown dwarf rather than a very low-mass star. This is called the lithium test, and it has been one of the key tools in the observational study of brown dwarfs since the 1990s. It is a lovely example of how astronomers use the internal physics of objects to infer their nature from the light they emit, reading the composition of an atmosphere through the subtle fingerprints of absorption lines, and inferring from those fingerprints something about the deep interior that no telescope can directly observe. The brief deuterium flame and the preserved lithium are, in a sense, the fingerprints of a brown dwarf's youth and the evidence of its nature. They tell the story of an object that briefly burned, that briefly participated in the nuclear reactions that defined stellar life, and then settled into a different kind of existence entirely. An existence defined not by burning, but by cooling. Not by brightness, but by patience. Not by the release of nuclear energy, but by the slow, steady dissipation of the heat that was there from the beginning. Let that image settle for a moment. The brief flame, the quiet extinction, and then the long cooling that follows. There is something in that sequence that resonates beyond the physics. Many things in the universe, and in life, have a brief, bright beginning that gives way to something longer, quieter, and ultimately more enduring. The drama of formation gives way to the steadiness of existence. The fire gives way to the warmth. And the warmth, as we will discover, lasts an almost incomprehensible length of time. For now, let the image of the deuterium flame rest in your mind. A small, quiet fire, burning for a few million years in the core of an object that will exist for 1 trillion more. A brief candle in a very long night. And then, gently, the candle goes out, and the real life of the brown dwarf begins. After the deuterium flame goes out, after the last of the nuclear reactions fade from the core of a brown dwarf, what remains is an object in the process of cooling. And cooling, in the context of a brown dwarf, is not a simple or a rapid thing. It is one of the most patient processes in the universe, a process so slow and so steady that it will continue long after every other significant event in the current chapter of cosmic history has come and gone. To understand what cooling means for a brown dwarf, we first need to understand what heat means inside one. When the brown dwarf formed, enormous amounts of gravitational potential energy were converted into thermal energy as the gas fell inward and compressed. Every kilogram of gas that fell toward the center added to the heat of the object, and by the time the brown dwarf reached its final, stable configuration, it had accumulated a vast reservoir of thermal energy. This energy is stored in the random motions of the gas particles inside the object. The faster they move, the higher the temperature, the more energy is stored. This stored heat is the only significant energy source a brown dwarf has after its deuterium burning ends. There is no fusion to replenish it. There is no ongoing gravitational contraction to add to it, because the electron degeneracy pressure has halted the contraction. The only thing happening is a slow, steady leakage of heat from the warm interior outward through the layers of the atmosphere and into the surrounding space. The rate at which this happens is governed by the opacity of the brown dwarf's interior and atmosphere, how easily or how reluctantly the material allows heat to flow through it. Dense, opaque materials are poor conductors of heat, which means they slow the cooling process. A brown dwarf is in many ways a very efficient insulator of its own interior warmth. The dense, compressed gas in its interior resists the rapid outward flow of heat, parceling it out slowly, reluctantly, over enormous stretches of time. In the early stages of cooling, when the brown dwarf is still relatively warm from its formation, the cooling is fastest. A newly formed brown dwarf might have a surface temperature of 2,000 degrees or more, hot enough to glow a dim reddish-orange. Over the first few 100 million years, it cools significantly, perhaps dropping to a surface temperature of around 1,000 degrees. This is still warm by human standards, hot enough to burn, hot enough to glow dull red in the infrared, but already far cooler than any true star. As billions of years pass, the cooling continues. The surface temperature drops below 1,000 degrees, into the range where the atmosphere's chemistry begins to change in fundamental ways. Molecules that were too energetic to survive at higher temperatures can now form and persist. The spectrum of the brown dwarf shifts, new absorption features appear, old ones fade, and the object's infrared glow becomes fainter and fainter. By the time a brown dwarf is several billion years old, perhaps the age of our solar system or older, its surface temperature may have dropped to 500 or 600 degrees. Still warm, still releasing heat, still faintly glowing in the mid-infrared, but already very difficult to detect even with sensitive telescopes at interstellar distances. Now consider what happens over 10 billion years. 20 billion. 100 billion. As the universe ages, as the current generation of stars burns through its fuel and eventually fades, the brown dwarfs that were formed alongside them will still be cooling, still releasing their stored heat, still faintly warm at their cores. The rate of cooling slows as the temperature drops, because cooler objects radiate less efficiently, and so the process stretches out further and further. Astronomers estimate that a brown dwarf of typical mass will take somewhere in the range of 10 to 100 trillion years to cool to temperatures approaching the cosmic background, the ambient temperature of the universe itself. 100 trillion years. The universe today is approximately 14 billion years old. 100 trillion is more than 7,000 times that age. It is genuinely impossible to develop any intuitive sense of this timescale. Every comparison falls short. If the current age of the universe were represented by a single day, 100 trillion years would be about 20 years. If you tried to represent 100 trillion years using grains of sand, and each grain represented 1,000 years, you would need enough sand to fill a large swimming pool. These comparisons help slightly, but they cannot really close the gap between the human sense of time and the patience of a cooling brown dwarf. what they can do is gesture towards something important. The universe we inhabit today, with its stars and galaxies and light and activity, is by cosmological standards an extremely young and unusually energetic place. The era of star formation, the period when gas collapses into stars and stars shine and scatter their material back into the galaxy, is a relatively brief episode in the full history of the universe. Within a few trillion years, the last new stars will have formed, and the existing ones will have exhausted their fuel. The universe will enter what cosmologists call the degenerate era, a long quiet period dominated not by burning stars, but by their cold remnants: white dwarfs, neutron stars, black holes, and brown dwarfs. In that era, brown dwarfs will be among the most significant objects in the universe. Not because they are active or energetic, but simply because they will be there, slowly cooling, still faintly warm, outlasting almost everything else. They will drift through a universe that has grown very dark and very quiet, moving in orbits around the fading cores of dead galaxies, encountering each other rarely, cooling by imperceptible degrees across incomprehensible spans of time. The image of that era is one of the most haunting in all of cosmology. A universe that has grown silent. The light's mostly out. The last red dwarf stars fading to white dwarf embers, and distributed across the vast dark spaces of what were once galaxies, the brown dwarfs, still barely glowing in the deep infrared, still carrying within them the warmth of their formation, patient beyond all reckoning. But we are getting ahead of ourselves. Right now, in the present universe, brown dwarfs are still in the relatively early stages of their cooling. Even the oldest ones, those that formed in the first billion years after the Big Bang, are still warm enough to detect with the right instruments. They are still releasing the heat accumulated during their formation, still faintly glowing, still visible to telescopes sensitive to infrared light. The cooling of a brown dwarf is not uniform throughout its bulk. The interior is always warmer than the surface because heat flows outward from inside to outside. There are temperature gradients within the object, layers of different temperatures stacked inside each other. Convection, the same process that stirs a pot of water on a stove, can operate in certain regions of the brown dwarf interior, carrying warm material upward and cooler material downward, mixing the layers and affecting how heat is transported toward the surface. The details of this internal structure matter for understanding the brown dwarf's evolution. They affect how quickly it cools, what its surface temperature and luminosity are at any given age, and what its atmosphere looks like. The atmosphere is where the interaction between the object and the outside universe takes place, and it is one of the most complex and fascinating aspects of brown dwarf science. But we will get to the atmosphere in its own time. For now, let the image of cooling be the thing you carry. The long, slow, extraordinarily patient release of heat that began at the moment of formation and will not end for trillions of years. Not a rapid cooling, not a dramatic collapse, not anything that would be visible to any human observer over a human lifetime. Just a steady, unhurried, inevitable flow of warmth from the interior of the brown dwarf into the surrounding space. Grain by grain, year by year, millennium by millennium, the heat drains away. The universe grows a little warmer by the tiniest imaginable fraction from each brown dwarf's contribution, and the brown dwarf itself grows a little cooler, a little dimmer, a little less detectable. And this process continues, and continues, and continues, long after the last of tonight's stars have gone dark. There is something almost meditative about that image. The slow, steady, patient cooling. The warmth persisting far longer than anyone might expect. The quiet endurance of an object that does not burn but simply is, releasing its warmth gradually into the dark, asking nothing in return, requiring nothing from the universe except the simple permission to exist and to cool. Let your own breathing match that patience for a moment. Not the urgency of the day that has just ended. Not the anticipation of the day that has not yet arrived. Just the slow, steady rhythm of breathing in and breathing out, releasing warmth into the room, patient and unhurried. Like the brown dwarf in the dark, like the warmth in the cold, like the long patience of a universe that has all the time it needs. Astronomers are, among other things, classifiers. They look at the universe and they organize it, assigning categories and labels and letters and numbers, building systems of order that allow the enormous diversity of cosmic objects to be discussed, compared, and studied. The stellar classification system that most people encounter, if they encounter any, is the one that assigns letters to stars based on their surface temperatures and spectral characteristics. The sequence runs O, B, A, F, G, K, M, remembered by generations of astronomy students through the mnemonic "Oh, be a fine girl, kiss me," or various other versions of that phrase that suit different preferences. Our own sun is a G-type star. The sequence runs from the hottest, most luminous O-type stars down through progressively cooler and dimmer types to M, which includes the cool red dwarf stars that are the most numerous true stars in the galaxy. For most of the history of modern astronomy, M was the end of the line. The coolest, dimmest, most unassuming category of star. But when brown dwarfs began to be discovered in significant numbers in the 1990s, it became clear that M was not enough. The new objects were cooler than any M dwarf star. Their spectra showed features that had never been seen in stellar objects before, and they clearly needed their own categories. And so the spectral sequence was extended, first with L, then with T, and eventually with Y, each new letter representing a cooler and dimmer category than the one before it. These three new spectral classes, L, T, and Y, are essentially the classification system for brown dwarfs, though the L class also includes the very coolest true stars, the low-mass red dwarfs that sit right at the stellar boundary. The T and Y classes are exclusively the domain of brown dwarfs and are among the most fascinating and alien-seeming categories of objects that astronomers study. Let us begin with the L dwarfs. These are the warmest of the brown dwarf classes, with surface temperatures ranging from roughly 2,000 degrees Celsius down to about 1,400 degrees. At these temperatures, the atmosphere is dominated by clouds of tiny mineral and metallite particles, things like iron droplets and silicate dust grains that condense out of the hot gas in the upper atmosphere and form thick, opaque cloud layers. The spectra of L dwarfs show strong absorption by metal hydrides, molecules like iron hydride and chromium hydride, and by water vapor and carbon monoxide. The light they emit is deep red to infrared, and they are among the most intrinsically faint objects detectable with current telescopes. L dwarfs represent the transition zone between the coolest true stars and the deeper brown dwarf territory. Some of them may actually be very low-mass stars that are fusing hydrogen at very low rates. Others are clearly substellar. Many are difficult to classify with certainty without knowing their age, because a younger, lower mass brown dwarf can have the same surface temperature as an older, higher mass one, since cooling takes different amounts of time depending on mass. The spectral type tells you the temperature. It does not by itself tell you the mass or the age. The T dwarfs are where things become distinctly alien. Surface temperatures in the T dwarf range run from about 1,400 degrees down to around 500 or 600 degrees. At these temperatures, the silicate and iron clouds that dominated the L dwarf atmospheres have largely sunk below the visible photosphere. The clouds are still there, deeper in the atmosphere, but the upper layers are clearer. What dominates instead is a molecule that feels very out of place in an astronomical context: methane. Methane is the molecule CH4, one carbon atom bonded to 4 hydrogen atoms. It is familiar on Earth as natural gas, as the compound that makes up the bulk of the gas burned in kitchens and furnaces. It is associated in the human mind with the cold, the damp, with swamps and landfills and the digestive systems of cattle. It is not, intuitively, something you expect to find in an astronomical object. And yet in the T dwarf range, methane forms readily in the cool upper atmosphere and creates characteristic absorption features in the infrared spectrum that are unmistakable. When astronomers first detected methane absorption in a brown dwarf candidate in 1995, it was a landmark moment. The object, now known as Gliese 229b, was confirmed as a brown dwarf, one of the first, and its methane-rich spectrum announced that here was something genuinely new, genuinely outside any previously known category of astronomical object. Methane in a star would be impossible. Methane in a planet would be unremarkable. Methane in a brown dwarf was revelatory, a sign that these objects occupied a truly intermediate domain, where planetary atmospheric chemistry and stellar structure overlapped. T dwarfs also show strong water vapor absorption, and their spectra are remarkably different from any true star. They are genuinely cool enough that their atmospheres behave more like the atmospheres of giant planets than like the atmospheres of stars. The chemistry of methane, water, ammonia, and other molecules that are unstable at higher temperatures begins to dominate. The physics of cloud formation and atmospheric circulation, the kinds of processes that create weather on Jupiter and Saturn, become relevant. And then there are the Y dwarfs, the coolest and most recently defined spectral class, with surface temperatures below about 500 degrees. Y dwarfs are the most extreme brown dwarfs currently known, the oldest and most thoroughly cooled, drifting through the galaxy as they slowly release the last reserves of their formation heat. Some of the coolest Y dwarfs have surface temperatures comparable to a warm oven, perhaps 200 or 300 degrees. Objects with such cool surfaces are extraordinarily faint. Their peak emission is so far into the infrared that detecting them at interstellar distances requires some of the most sensitive infrared instruments ever built. The discovery of Y dwarfs became possible largely through the Wide Field Infrared Survey Explorer, or WISE, a space telescope launched in 2009 that mapped the entire sky in the infrared. WISE was sensitive enough to detect the faint warmth of Y dwarfs at distances of tens of light years from the Sun, and it found dozens of them, some of which turned out to be among the nearest neighbors of our solar system yet discovered, so close and yet so invisible to previous surveys that they had been completely overlooked. One of the most striking discoveries from these infrared surveys has been just how many brown dwarfs are lurking in the solar neighborhood. Within about 30 light years of the Sun, which is a relatively small volume of space on galactic scales, astronomers have found dozens of brown dwarfs. Some estimates suggest that brown dwarfs may be nearly as common as true stars in the galaxy, and possibly more common. The exact ratio is still uncertain because the faintest and coolest brown dwarfs are so difficult to detect that our census of them is certainly incomplete. But the emerging picture is one of a galaxy where brown dwarfs are not rare exceptions, but extremely numerous members of the stellar community, perhaps billions of them drifting through the Milky Way at this very moment. The spectral sequence L-T-Y is not just a classification tool. It is a timeline. A brown dwarf that forms as a warm L dwarf will, over billions of years, cool into the T dwarf range and eventually into the Y dwarf range. The spectral class tells you not just the temperature but the age, at least in a rough way. Warmer means younger, cooler means older. The L dwarfs we observe today are younger objects still radiating the heat of their formation. The coolest Y dwarfs are ancient objects, formed perhaps when the universe was young, now in the late stages of their slow cooling, drifting quietly through the galaxy in the deep infrared. The James Webb Space Telescope, which began science operations in 2022, has opened new windows on brown dwarfs. Its extraordinary sensitivity in the infrared means it can detect and characterize brown dwarfs that were previously little more than faint detections, and it has the capability to detect Y dwarfs at greater distances than any previous instrument. Some of the early scientific results from JWST have included detailed spectroscopic characterization of brown dwarf atmospheres, revealing the chemistry and physics of these alien environments in unprecedented detail. What has emerged is a picture of extraordinary complexity and richness, atmospheres full of clouds and chemistry that behave in ways both familiar and deeply strange. The letters L, T, and Y are quiet letters. They do not carry the drama of O and B, the blazing hot massive stars that light up nebulae and explode as supernovas. They do not carry even the modest familiarity of G, the class of our own sun. They are the end of the alphabet, the cool end of the spectrum, the letters that were added as an afterthought because the universe turned out to contain more than the original sequence anticipated. But those quiet letters represent billions of objects. They represent a vast population of the galaxy that was invisible to us for most of human history. They represent the cool, patient, enduring majority of a universe that we have been looking at through a very narrow and very bright window. When we learn to look through the infrared window, when we train our instruments on the faint warmth of L and T and Y dwarfs, we find a universe that is much more populated than the bright stars led us to believe. The night sky of the infrared is a different sky than the one our eyes see. It is a sky crowded with cool, dim objects, a sky where the brown dwarfs reveal themselves as the numerous, patient, enduring inhabitants they have always been. And once you know they are there, once the classification system and the infrared surveys and the spectral letters have oriented you, you begin to see the familiar night sky differently. Not as a record of all that is there, but as a single luminous layer over a much deeper and much more populated dark. If you could somehow travel to a brown dwarf and look up from its surface, what would you see? This is an unusual question to ask about an astronomical object, because most astronomical objects do not have surfaces in any meaningful sense, and most do not have anything resembling a sky. Black holes have no surface. Neutron stars have surfaces so extreme that the concept of looking up from them is physically meaningless. Even our own sun has no solid surface, just a region where the gas becomes dense enough that its light cannot escape from within. But a brown dwarf is different. A brown dwarf has an atmosphere, a layered envelope of gas that surrounds the denser interior, with conditions that change from layer to layer, with chemistry that varies with altitude and temperature. And while no human will ever stand on a brown dwarf or anywhere near one, the question of what its sky looks like is not merely fanciful. It is a genuine scientific question, one that atmospheric physicists and planetary scientists have been working to answer using observations, theoretical models, and computer simulations. What they have found is that the skies of brown dwarfs are among the most alien and most dramatic environments known in the universe. Let us begin with the clouds. Because the skies of brown dwarfs are, above almost everything else, cloudy. Not cloudy in the way that Earth is cloudy on an overcast day, with white water vapor clouds drifting through a blue sky, but cloudy in ways that require entirely new vocabulary, new physics, and new imagination to understand. In the L dwarf range, the warmest brown dwarfs, the clouds are made of minerals and metals. Silicate clouds form from the condensation of silicon and oxygen compounds, tiny grains of material similar in composition to sand on Earth, but forming in the upper atmosphere of a substellar object rather than on a beach. Iron clouds, made of actual metallic iron that has condensed out of the hot gas, drift through the atmosphere in layers. Corundum, which on Earth forms rubies and sapphires, can condense in the upper layers of L dwarf atmospheres. Imagine looking up through an atmosphere where the clouds are made of iron and ruby, where the weather is not a matter of water falling from the sky, but of iron droplets, silicate particles, and mineral grains forming and falling and re-evaporating as they descend into warmer layers. Where the sky has a deep reddish-brown cast from the combined absorption of all these metal-rich cloud layers, and where the light that filters through is deep red and infrared, not the broad white light of a sun-illuminated sky. For those brown dwarfs that are not in binary systems and do not have their own illuminating companion, there would be no external light source at all. The faint glow would come from the brown dwarf itself, from the warmth seeping upward through the atmosphere from the interior. The sky would be lit from below, in a sense, the interior warmth diffusing upward through the cloudy layers and creating a dim, reddish, deeply infrared illumination unlike anything in human experience. The clouds in L dwarf atmospheres are not passive. They are dynamic, driven by powerful atmospheric circulation that is in some ways even more vigorous than what we see on Jupiter and Saturn. Brown dwarfs rotate rapidly, many of them completing a full rotation in under 12 hours, some in just a few hours. This rapid rotation creates strong Coriolis forces that organize the atmospheric circulation into bands and jets, similar to the banded structure visible on Jupiter, but potentially more extreme given the brown dwarf's greater gravity and rotation rate. Astronomers have been able to detect this banding and the associated variability by monitoring the brightness of brown dwarfs over time. As a brown dwarf rotates, different portions of its atmosphere rotate into view, and if those portions have different cloud thicknesses or different temperatures, the brightness varies with the rotation period. By tracking these brightness variations, astronomers can measure the rotation rate of brown dwarfs and infer something about the large-scale structure of their cloud patterns. Some brown dwarfs show dramatic variability, changing in brightness by 10 or 20% over the course of a single rotation. Others are relatively stable. The most variable ones are thought to have patchy cloud cover, with thick cloud regions alternating with clearer areas that allow deeper, hotter layers of the atmosphere to contribute more flux to the observed brightness. This patchy structure is thought to arise from the complex dynamics of cloud formation and disruption in a rapidly rotating, turbulent atmosphere. When we move into the T-dwarf range, cooler and older, the atmosphere changes fundamentally. The silicate and iron clouds that dominated the L-dwarf spectral region sink below the visible photosphere as the atmosphere cools. The upper atmosphere clears, and what had been a murky, cloud-shrouded sky becomes clearer. But what fills that cleared sky is methane. Methane clouds in T-dwarfs are a concept that still startles astronomers who work on planetary atmospheres, because methane behaves very differently from silicate or iron. It forms not through condensation of a high-temperature mineral, but through chemical reactions between carbon and hydrogen atoms in the cool upper atmosphere. The presence of methane means that the chemistry of the atmosphere has crossed into a regime more like that of a cold giant planet than a warm stellar object. The sky of a T-dwarf would be permeated with this methane atmosphere, a pall of hydrocarbon chemistry hanging over an environment that is already dim and alien. The temperature might be comparable to a very hot summer day on Earth, perhaps 500 to 1,000 degrees, and yet the object is an astronomical body with tens of Jupiter masses and the structural properties of a would-be star. The collision of these scales, the near-human temperature with the astronomical mass, makes T-dwarfs feel particularly strange when you try to hold both facts in mind at once. Below the methane layer, in the T-dwarf atmosphere, there would still be clouds of water ice. Water ice, the same material that forms snowflakes on Earth, can condense in the upper atmosphere of T-dwarfs, creating ice clouds at altitudes where the temperature drops below the freezing point of water. The idea of water ice clouds on a brown dwarf is one of those details that illustrates how the universe enjoys mixing contexts that our intuitions want to keep separate. Ice crystals, the material of blizzards and glaciers, drifting in clouds around an object that contains 80 times the mass of Jupiter. The white dwarfs, the coolest known brown dwarfs with surface temperatures below 500 degrees, may have even more exotic cloud chemistry. At these temperatures, ammonia can condense, forming ammonia ice clouds similar to those seen in Jupiter's upper atmosphere. Some models also predict the formation of water droplet clouds, actual liquid water clouds, in the atmospheres of the coolest white dwarfs. The surface temperature would be similar to that of a moderate oven, and in the upper atmosphere, where temperatures are cooler, liquid water could potentially condense. This is a remarkable thought. Liquid water, the substance most closely associated with life on Earth, potentially forming as cloud droplets in the atmosphere of a brown dwarf. Not on a surface, not in an ocean, but in the suspended droplet form of cloud, drifting through the cool upper atmosphere of an object that is simultaneously planetary in some ways and stellar in others. No one is suggesting that life exists in brown dwarf atmospheres. The conditions are challenging in many ways beyond just the presence of water. There is no stable surface, enormous pressure gradients, powerful gravitational fields, complex hydrocarbon chemistry, and a permanent darkness that only the faintest infrared glow interrupts. But the presence of liquid water clouds is a reminder that the ingredients for interesting chemistry exist in places and contexts that we would not intuitively associate with them. The weather on a brown dwarf is also not a calm affair. Beyond the cloud variability driven by rotation, there are likely storm systems, vortices, and large-scale turbulence that would dwarf anything in our solar system. The great storm known as Jupiter's Great Red Spot, which has been raging for at least several centuries and is wider than the Earth, would be a modest disturbance compared to what may be possible on a rapidly rotating, massive brown dwarf. Some theorists have proposed that large-scale vortices or storm systems could persist on brown dwarfs for millions or even billions of years, driven by the continuous release of heat from the interior. There is also the question of lightning. On Earth, Jupiter, Saturn, and Uranus, lightning is a product of the vigorous atmospheric circulation that separates electrical charges in cloud layers. On a brown dwarf, with its powerful circulation, its mineral and metal clouds, and its complex chemistry, the conditions for lightning seem even more extreme. The lightning strokes on brown dwarfs, if they occur as models suggest, would be enormous by terrestrial standards, discharging across hundreds of kilometers of atmosphere, releasing energy that dwarfs the most powerful terrestrial storms. None of this weather is observable in real time with current instruments. What we see from Earth is the integrated light of the whole visible atmosphere, the combined effect of all the cloud layers and temperature structures averaging out into a single infrared signal. The variability measurements give us some information about the large-scale cloud patterns, but the details of the weather, the storms, the lightning, the rainfall of iron and silicate remain inferred from models rather than directly observed. This is one of the fascinating aspects of brown dwarf science. So much of what we understand is inferential. We measure the light that arrives at our telescopes, and from it we infer the temperature, the composition, the cloud structure, the rotation rate, the age. The actual environment, the strange and alien sky of a brown dwarf, remains at the end of a chain of inference rather than at the end of a camera pointed directly at it. But inference, when it is grounded in good physics and good observation, can be extraordinarily reliable. We are confident that the methane clouds are there, that the iron rain happens, that the mineral clouds form and clear with the brown dwarf's rotation, because the spectroscopic evidence is unambiguous and the models that reproduce it are consistent. The strange skies of brown dwarfs are real, even if they have never been photographed. Let that image drift through your mind as your eyes grow heavy. A sky of iron and silicate clouds, lit from below by the faint glow of a slowly cooling interior. No starlight from outside, no blue sky, no sunsets, only the deep reddish dark of an alien atmosphere. And far above, if you could somehow rise through the cloud layers to the top of the atmosphere, only the faint warmth of infrared light trickling outward into the cold of space. A sky unlike any other. A sky belonging to one of the quietest, most patient, most enduring objects in the universe. A sky worth drifting through, in the imagination, on the way to sleep. Everything warm glows. This is one of the most fundamental facts in physics, a consequence of the behavior of matter at any temperature above absolute zero. Whether it is a cup of hot tea, a human body, a warm sidewalk after sunset, or the smoldering core of a brown dwarf drifting through the galaxy, any object with heat above the absolute minimum will radiate that heat as electromagnetic waves. The temperature of the object determines what kind of radiation it emits, what wavelengths dominate, how much energy flows outward per second. For very hot objects, like the surface of the sun at about 5,500 degrees Celsius, the peak of the radiation falls in the visible part of the spectrum. This is why the sun looks white or pale yellow, why it illuminates the world in a broad range of colors. The sun's surface temperature is such that it emits most of its energy precisely in the narrow band of wavelengths that human eyes evolved to detect. This is not a coincidence. Life on Earth evolved under sunlight, and eyes that were sensitive to the wavelengths that sunlight provides were enormously useful. Our visual range is, in a very real sense, tuned to our star. For cooler objects, the peak of the radiation shifts toward longer wavelengths, toward the infrared. An object at several hundred degrees, like a warm stove, emits mostly in the near-infrared, where heat-sensitive instruments can detect it, but eyes cannot. An object at human body temperature emits in the mid-infrared. An object as cool as a room emits in the far infrared. Brown dwarfs, with surface temperatures ranging from around 2,000 degrees for the warmest L dwarfs down to perhaps 200 degrees for the coolest white dwarfs, emit most of their radiation in the infrared. The warmer ones emit in the near-infrared, just beyond the red end of the visible spectrum. The cooler ones emit further into the infrared, in wavelengths that correspond to what we normally think of as radiant heat. This is why brown dwarfs were essentially invisible to classical optical astronomy. Telescopes that collect visible light, whether they are the naked human eye or a large ground-based optical telescope, simply do not see the wavelengths where brown dwarfs shine. The brown dwarfs were there all along, radiating their warmth into the galaxy, but in a language that human eyes cannot speak. The development of infrared astronomy over the latter half of the 20th century was, in a very literal sense, the opening of a new window on the universe. Infrared detectors, cooled to cryogenic temperatures so that their own thermal radiation would not overwhelm the faint signals they were trying to measure, began to reveal a universe invisible to optical telescopes. Not just brown dwarfs, but the centers of galaxies obscured by dust, young stars still embedded in their birth clouds, the chemical signatures of molecules in interstellar space. Infrared astronomy transformed our understanding of the cosmos precisely because it showed us what visible light astronomy had been missing. For brown dwarfs, the infrared glow is the primary signature, the main evidence of their existence. When a brown dwarf is observed through an infrared telescope, it appears as a point source of light, much like a star appears in a visible telescope. But the color, or more precisely the ratio of brightness at different infrared wavelengths, tells a story very different from any star. The spectrum shows the deep absorption bands of water vapor, methane, ammonia, and other molecules that define the T and Y dwarf spectral classes. It shows the reddened colors of iron and silicate cloud layers in the L dwarfs. It shows, in short, the temperature and the chemistry of an object that is doing something fundamentally different from nuclear burning. The infrared glow of a brown dwarf is not a constant thing. It changes over time as the brown dwarf cools. A newly formed brown dwarf, still warm from its formation, glows brightly in the near-infrared. As it cools over millions and billions of years, its peak emission shifts further into the infrared and its total luminosity decreases. Astronomers can use this cooling track, the predictable way in which luminosity and color change with age and mass, to estimate the age of a brown dwarf if its mass is known, or to estimate the mass if the age is known. This technique of reading the age in the infrared glow requires knowing something about the history of the object, which is not always possible. Isolated brown dwarfs, drifting alone through the galaxy, carry no birth certificate. But brown dwarfs that are members of clusters, groups of stars that all formed at roughly the same time from the same cloud of gas, do carry that context. By observing brown dwarfs in clusters of known age, astronomers can calibrate the cooling tracks and build a more reliable understanding of how the infrared glow evolves over time. There is a particular quality to the infrared glow of brown dwarfs that is worth dwelling on. It is not borrowed light, not reflected starlight, not the product of any external energy source. It is intrinsic. It is the brown dwarf's own stored warmth, its own thermal energy, flowing outward through the layers of its atmosphere and escaping into space. Every photon of infrared light that leaves a brown dwarf represents a tiny subtraction from its internal energy store, a microscopic step forward in its cooling. This intrinsic glow is a kind of testimony. It testifies to the formation event, to the tremendous energy that was deposited when a cloud of gas collapsed under gravity and compressed itself into the dense, compact object the brown dwarf now is. That energy has been stored, parceled out slowly, released photon by photon into the surrounding dark. The infrared glow is the residue of a formation that happened long ago. For the oldest brown dwarfs, it is the residue of a formation that happened billions of years ago, when the universe was young and the Milky Way was still assembling itself from the collisions and mergers of smaller proto-galactic systems. Consider what it means that some of the brown dwarfs drifting through the galaxy today formed when the universe was only 1 billion or 2 billion years old. The universe is currently about 14 billion years old. Those ancient brown dwarfs have been cooling for 12 or 13 billion years, longer than Earth has existed, longer than our sun has burned. They have watched entire stellar generations pass. They have drifted through a galaxy that has changed dramatically around them, stars forming and dying, spiral arms rotating, the Milky Way colliding and merging with smaller galaxies. Through all of it, they have simply been there, glowing faintly in the infrared, cooling by imperceptible degrees. The infrared glow is also what allows us to find these ancient objects. Even after billions of years of cooling, even after a T or Y dwarf has faded to a surface temperature of a few hundred degrees, it is still warm enough to emit detectably in the mid-infrared, at least if it is not too far away. The WISE satellite, with its sensitivity to mid-infrared wavelengths, found brown dwarfs so cold that their surface temperatures are comparable to a warm summer day on Earth. Objects at those temperatures, at the distances of nearby stars, are extraordinarily faint. But they are not invisible. Their infrared glow, faint as it is, still carries enough photons across the light years to trigger a sensitive detector. The James Webb Space Telescope has pushed this further. With its massive mirror and its exquisite infrared sensitivity, it can detect and characterize brown dwarfs that WISE could only barely glimpse, or not at all. The mid-infrared camera on JWST, known as MIRI, operates at wavelengths where the coolest Y dwarfs emit most of their light, making it the ideal instrument for studying these extreme objects. Some of the earliest science programs with JWST targeted brown dwarfs specifically, recognizing that these objects would be among the most rewarding for a telescope of its capabilities. The results have been illuminating in the infrared sense. JWST spectroscopy of T and Y dwarfs has revealed atmospheric chemistry in more detail than was previously possible, confirming the presence of methane and water, detecting signatures of carbon dioxide and carbon monoxide, and finding evidence for chemical disequilibrium, meaning that the atmosphere is not in its lowest energy chemical state, because mixing and circulation are continuously moving material from deeper, hotter layers where the chemistry is different up to cooler layers where it has not had time to re-equilibrate. This chemical disequilibrium is itself a kind of testimony to the internal dynamics of the brown dwarf. It says that the atmosphere is not static, that material is being moved around, that there is a connection between the deep interior and the visible surface layer. It is evidence for the convection and circulation that models have predicted for decades, now finally seen directly in the spectra of real objects. The infrared glow is, in the end, a form of communication. It is how brown dwarfs speak to us across the vast distances of space. Unable to shine in visible light, unable to announce themselves in the wavelengths our eyes were built for, they broadcast their presence in a quieter channel, in the warmth that seeps outward through their atmospheric layers and travels across the light years as infrared photons. We needed to build the right receivers, the right cooled detectors, the right space telescopes, before we could hear that broadcast. But once we built them, the universe revealed that these quiet objects were everywhere, their infrared voices filling the galactic background, patient and persistent and never silent. Let that image accompany you as your body grows heavier and your thoughts grow softer. All around the galaxy, in the warm infrared, brown dwarfs glow. Billions of them, perhaps. Each one a slow ember in the dark, broadcasting its warmth in wavelengths human eyes cannot see, patient and persistent in the cold spaces between the stars. Their glow has been there all along. We simply had not yet learned to listen. There is a particular kind of satisfaction that comes from finding something that was hidden. Not hidden deliberately, not concealed by any intention, but hidden simply because the tools available were not suited to the task of finding it. Hidden the way a radio signal is hidden from someone without a radio, or the way ultraviolet light is hidden from eyes that evolved under visible light conditions. The thing is there, broadcasting its presence in every direction. The problem is not the object. The problem is the receiver. This is exactly the situation that astronomers faced with brown dwarfs for most of the 20th century. The theory was in place long before the detections. As early as the 1960s, theoretical astronomers working on the low end of the stellar mass function began to realize that the laws of physics should permit objects to exist between the mass of Jupiter and the mass of the smallest true stars. The physics of gravitational collapse, the physics of electron degeneracy pressure, the physics of nuclear fusion thresholds, all pointed toward the same conclusion. There ought to be a population of substellar objects drifting through the galaxy, too small to sustain hydrogen fusion, too large to be classified as planets, existing in a regime that no known object occupied. But knowing something ought to exist and actually finding it are very different things. The predicted objects would be faint, extraordinarily faint by the standards of stellar astronomy. They would emit most of their light in the infrared rather than in visible wavelengths. And crucially, astronomers did not yet have the tools to search for them systematically. The infrared detectors of the 1960s and 1970s were primitive by modern standards, capable of detecting the brightest infrared sources but utterly blind to the faint glow of a cool brown dwarf at interstellar distances. The search for brown dwarfs became one of the long-running quests in observational astronomy, a decades-long effort to find objects that had to be there but could not be caught. False alarms accumulated. Objects were announced as brown dwarf candidates and then reclassified. The community grew cautious, skeptical of claimed detections, aware of how easy it was to misidentify a faint, cool, unusual-seeming object. The first confirmed brown dwarfs arrived almost simultaneously in 1995, and they came from two different directions, which gave the confirmations extra weight. One was Gliese 229b, discovered as a faint companion to a nearby M-dwarf star. It was found by direct imaging, which means astronomers actually took a picture of it, a small feint that next to its brighter companion. Its spectrum, taken shortly after its discovery, showed the unmistakable methane absorption bands that confirmed it as a T-dwarf, too cool and too methane-rich to be any kind of star. The other was Tide 1, found in the Pleiades cluster, identified as a brown dwarf through a combination of its luminosity and its lithium content. The lithium test confirmed that Tide 1 had not destroyed its lithium through nuclear reactions, meaning it had never been hot enough to do so, meaning it was substellar. These two confirmations, arriving within months of each other, opened the floodgates. The community had been holding its breath for decades, and suddenly the brown dwarfs were real, confirmed, present in the data. The question shifted from whether they existed to how many there were, and where they were, and what they were like. The answer to how many came quickly as better infrared surveys began. The 2-micron all-sky survey, known as 2MASS, mapped the entire sky in 3 near-infrared bands during the late 1990s and early 2000s. It found hundreds of L and T dwarfs, many of them within a few tens of light years of the Sun. The Deep Near-Infrared Survey of the Southern Sky, known as DNIS, added more. The Sloan Digital Sky Survey, primarily an optical survey, but with some infrared coverage, contributed. Within a few years of the first confirmed brown dwarfs, the population had grown from a handful to hundreds. But the brown dwarfs found in these surveys were the relatively warm ones, the L dwarfs and the early T dwarfs, objects warm enough to be detectable in near-infrared bands. The cooler, older, fainter T dwarfs and the Y dwarfs that theorists predicted should exist remained largely out of reach. Finding them required going deeper into the infrared, to mid-infrared wavelengths where the coolest brown dwarfs emit most of their light. And that meant going to space. The Spitzer Space Telescope, launched in 2003 and operating until 2020, was a major step forward. Spitzer operated in the mid and far infrared, wavelengths impossible to observe from the ground because Earth's own atmosphere absorbs them. From its vantage point above the atmosphere, Spitzer could detect the faint mid-infrared glow of cool brown dwarfs and characterize their atmospheric properties through spectroscopy. It found late T dwarfs, characterized their methane absorption, measured their luminosities, and pushed the observational boundaries further toward the cool end. But the truly transformative survey was WISE, the Wide Field Infrared Survey Explorer, which operated from 2010 to 2011 and then in a reactivated extended mission. WISE mapped the entire sky in 4 mid-infrared bands, with sensitivity far exceeding any previous all-sky infrared survey. It was specifically designed to find cool brown dwarfs, among other targets, and it delivered spectacularly. WISE found dozens of white dwarfs, the coldest class, objects with surface temperatures in some cases below 300 degrees. It found brown dwarfs so close to the Sun that they were among the nearest known stellar or substellar neighbors, yet had been completely missed by previous surveys because they were invisible to optical instruments. One of the most striking WISE discoveries was the binary system WISE 10495319, now known informally as Lumen 16, a pair of brown dwarfs only about 6.5 light-years from the Sun. This made them the third nearest known system to the solar system, after Alpha Centauri and Barnard's star. They had been there all along, only 6.5 light-years away, and we had not noticed them until a mid-infrared survey finally looked in the right wavelengths. The fact that such near neighbors could be discovered so recently says something profound about the incompleteness of our census of the solar neighborhood, and about how much of the universe has been hidden in plain sight simply because we were looking in the wrong colors. Finding brown dwarfs requires not just the right instruments, but also the right techniques. Because brown dwarfs are so faint and so numerous in the infrared sky, distinguishing them from other faint infrared sources, distant galaxies, dust clouds, variable stars seen through extinction, requires careful analysis. Astronomers use the colors of objects, the ratios of brightness at different infrared wavelengths, as a first filter. Brown dwarfs have characteristic colors that differ from galaxies and most other objects. Follow-up spectroscopy then confirms the classification, showing the methane and water absorption features that define the spectral type. Proper motion measurements have also been essential. Brown dwarfs in the solar neighborhood are moving through space relative to the background of distant stars and galaxies. This motion, called proper motion, causes nearby objects to shift their apparent position on the sky over months and years. By comparing images taken at different times, astronomers can identify objects with significant proper motion and flag them as potentially nearby. Brown dwarfs, being intrinsically faint, are almost always only detectable when they are relatively close, so objects with measurable proper motion are promising candidates. The combination of infrared photometry, spectroscopy, and proper motion measurements has built up a census of brown dwarfs in the solar neighborhood that is probably close to complete for objects warmer than about 500 degrees within roughly 30 light-years. Beyond that distance, and for cooler objects, the census is increasingly incomplete. The James Webb Space Telescope is beginning to extend this census further, finding cool white dwarfs at greater distances and characterizing them in more detail than was previously possible. There is something philosophically interesting about the process of finding what cannot be seen. It requires a kind of scientific imagination that is not just about building better tools, though it is certainly that. It is also about being willing to look in unfamiliar directions, to listen on channels that are not the obvious ones, to take seriously the possibility that the universe contains significant things that your current instruments are simply unable to detect. In the case of brown dwarfs, astronomers knew for decades that the objects had to be there. The physics demanded it. But translating that theoretical certainty into observational reality required patience, engineering, creativity, and a willingness to keep trying despite the long series of false alarms and near misses. The confirmation in 1995 was not a sudden discovery, but the culmination of a long and careful process of building the right tools and developing the right methods. This is, in a sense, a parable about the nature of knowledge. The universe does not always make itself easy to find. Some of its most numerous and most patient inhabitants are the least obvious, the least willing to announce themselves in the wavelengths we happen to be sensitive to. Finding them requires effort, ingenuity, and the willingness to extend our senses into domains that are not naturally accessible. When we do, when we build the infrared detectors and the space telescopes and the proper motion surveys, the universe opens up and reveals that it was always fuller than it appeared. Brown dwarfs were always there. In the 1960s, drifting through the galaxy in their billions, they were as present as they are today. The astronomers of that era walked under skies full of their invisible infrared glow, looked up at the bright stars that their instruments could detect, and could not know that all around those bright stars, in greater numbers than the stars themselves, the quiet ones were drifting. It took 30 years of effort to develop the eyes to see them. And once we did, the night became far more crowded than it had seemed. In the galaxy, as in life, some objects travel alone and some travel with companions. Stars form in clusters, in groups, in binary and triple and quadruple systems. They form close together and then drift apart, or they remain bound to each other by gravity for billions of years, orbiting a common center of mass in a slow gravitational dance that persists long after the cloud they formed from has dispersed. The statistical tendency of stars to form in pairs or groups is well established. Roughly half of all Sun-like stars are thought to be in binary systems, orbiting a companion. For massive stars, the fraction is even higher. Brown dwarfs, forming through the same cloud collapse process as stars, might be expected to follow similar patterns. And in many ways they do. Brown dwarfs are found as companions to stars, orbiting at various distances, detected by the ways their gravitational influence affects the star or by direct imaging when they are far enough from the star's glare to be seen. Brown dwarfs are found as companions to other brown dwarfs, forming binary pairs where both members are substellar. And brown dwarfs are found as isolated objects, alone in the galaxy, drifting without any companion at all. Each of these configurations has its own character, its own implications for the brown dwarf's existence, and its own contribution to our understanding of how these objects form and evolve. The brown dwarfs found as companions to stars are perhaps the most straightforwardly detectable, at least when they are not too close to their host star. Gliese 229b, one of the first confirmed brown dwarfs, was found precisely because it was orbiting a nearby star at a distance large enough to be separated from the star's glare with a good telescope. Other brown dwarf companions have been found through the radial velocity technique, which detects the tiny wobble a companion induces in a star's motion toward and away from Earth as they orbit each other. And some have been found through microlensing, a technique that detects the brief brightening of a background star when a foreground object's gravity bends and focuses its light. But studying brown dwarf companions to stars has revealed a curious pattern. Brown dwarfs are surprisingly rare as close companions to Sun-like stars. When astronomers survey Sun-like stars for companions at orbital distances similar to those of the inner planets, they find other stars at a certain rate, and they find giant planets at a certain rate, but they find brown dwarfs at a much lower rate than either. This absence has been called the brown dwarf desert, and it is one of the most intriguing statistical features of the brown dwarf population. At larger orbital distances, the brown dwarf desert disappears. Brown dwarfs are found as wide companions to stars at distances of hundreds of astronomical units, the kind of separations where the designation companion is almost a formality, where the two objects are gravitationally bound but barely interactive. And at very large separations, brown dwarfs are found that might more properly be called co-formed objects than companions, objects that formed from the same gas cloud as a nearby star, but at enough distance that the gravitational relationship is weak. The result is a deficit at close separations. The brown dwarf desert remains not fully explained. One possibility is that it reflects the physics of planetary formation. Close-in planets form through a process of gradual accretion in a protoplanetary disk, and this process favors objects up to about 10 Jupiter masses before some instability disrupts further growth. True stellar companions form through direct fragmentation of the parent gas cloud. Brown dwarfs in the intermediate mass range and at close orbital distances may fall in a zone where neither process operates efficiently. They are too massive to form readily by accretion and too light to form easily by the fragmentation process that makes close stellar companions. The result is a deficit at close separations. Brown dwarf binaries, systems where two brown dwarfs orbit each other, are a particularly interesting population. They tend to be found at fairly close separations, typically within a few astronomical units of each other, and they tend to have mass ratios close to 1, meaning the two members are often of similar mass. This is quite different from stellar binaries, which can have very unequal masses and a wide range of separations. The tendency of brown dwarf binaries to have similar masses is thought to reflect their formation process. When a cloud fragment collapses and forms two brown dwarfs rather than one, the material available is divided between them, and there appears to be a tendency for the division to be roughly equal. The physics of cloud fragmentation at the low mass end seems to favor roughly equal mass products. This is an active area of research, and the precise mechanism is not fully understood, but the observational pattern is clear. Lumen 16, the nearby binary discovered by WISE, is a beautiful example of a brown dwarf binary. The two components, Lumen 16A and Lumen 16B, are separated by only about 3 astronomical units, roughly the distance from the Sun to the asteroid belt. Lumen 16A is an L dwarf and Lumen 16B is a T dwarf, meaning the two objects have different surface temperatures despite forming from the same cloud at the same time. The difference in spectral type reflects a difference in mass. The slightly more massive member has cooled more slowly and therefore remains warmer. By studying both members of such a binary, astronomers can directly compare objects of the same age but different masses, providing a kind of controlled experiment that constrains the cooling models. Lumen 16b has been particularly well studied and has revealed something remarkable. It is a dramatically variable object. As it rotates, its brightness changes by several percent, indicating large-scale patchy cloud structures that rotate in and out of view. The variability patterns in Lumen 16b have been mapped in considerable detail, revealing something like a great storm system or a large clearing in the cloud deck that rotates around the brown dwarf, creating a regular pattern of brightening and dimming that repeats with the rotation period of about 5 hours. This variability has been observed simultaneously from multiple telescopes, including Hubble and Spitzer, allowing scientists to probe the cloud structure in different wavelength bands and build up a three-dimensional picture of the atmosphere. The isolated brown dwarfs, those with no stellar companions, present a different set of questions. How did they come to be alone? One possibility is that they formed in isolation from small, low-mass cloud fragments that collapsed without forming companions. Another possibility is that they formed in binary or multiple systems and were subsequently ejected through dynamical interactions. Young star-forming regions are chaotic places where newly formed objects interact gravitationally, and the least massive members can be flung out of the cluster entirely by close encounters with more massive objects. An ejected brown dwarf would then travel through the galaxy as an isolated object, its history of companionship erased, its trajectory determined by whatever gravitational kick it received during the ejection. Some isolated brown dwarfs may also be free-floating planetary mass objects, formed in protoplanetary disks around stars, and then ejected by gravitational interactions with other planets in the system. These objects, sometimes called rogue planets or free-floating planets, are genuinely at the boundary between planet and brown dwarf, and whether they should be classified as one or the other depends partly on how they formed rather than purely on their mass. The question of companionship for brown dwarfs has a dimension beyond the purely statistical and astrophysical. There is something in the image of an isolated brown dwarf drifting through the galaxy alone that resonates with the philosophical themes of this night's exploration. An object that formed in the same way as stars and perhaps as companions, that may have once been part of a system and now travels alone through the dark, cooling slowly, glowing faintly, encountering other objects only through the weakest gravitational whispers. And yet, even the isolated brown dwarf is not truly alone in the deepest sense. It is embedded in the galaxy, subject to the galaxy's gravitational field, participating in the great rotation of the Milky Way around its center. It passes through regions of higher and lower stellar density, occasionally making close approaches to other stars or brown dwarfs that alter its trajectory by tiny amounts. Over billions of years, the accumulated effect of these gravitational nudges shapes its orbit in ways that no simple prediction could track. It is solitary but not disconnected. It moves in a web of gravitational relationships that spans the entire galaxy. This is perhaps true of many things that appear alone. The appearance of isolation is rarely the whole story. The isolated brown dwarf, the one that travels without a stellar companion, is still part of the larger community of the galaxy, still subject to the forces that bind the Milky Way together, still contributing its faint infrared glow to the total energy budget of the cosmos. Its solitude is real but not absolute. It is alone the way any traveler is alone on a long journey through a populated landscape, moving without immediate company, but always within a larger context of connection. We touched on it briefly in the previous part, that curious gap in the population of companions to sun-like stars, the zone of orbital distances and mass ranges where brown dwarfs are found far less often than statistics would suggest they should be. Astronomers call this the brown dwarf desert, and it is worth spending more time in it, not just as an observational curiosity, but as a window into the deeper physics of how objects form in the crowded environment of a collapsing star system. The phrase brown dwarf desert conjures a particular image: a landscape of absence, a region that looks, from a distance, as though it should be populated but which turns out, on closer inspection, to be nearly empty. Actual deserts on Earth are not without life, of course. They harbor specialized organisms that have adapted to conditions of scarcity, and they have their own austere beauty. But the absence of the lush populations that occupy other landscapes is real and striking. The brown dwarf desert has a similar quality. It is a region of parameter space, defined by orbital separation and mass, where the expected population is simply not there. The discovery of the brown dwarf desert emerged from large radial velocity surveys of nearby stars. These surveys, which monitor the spectra of hundreds or thousands of stars looking for the Doppler shifts that indicate the presence of a gravitational companion, accumulated enough data by the late 1990s and early 2000s to characterize the statistical distribution of companion masses. What they found was striking. Stellar companions, those above about 80 Jupiter masses, are found orbiting Sun-like stars with a certain frequency, particularly at separations of a few astronomical units. Giant planets, those in the range of 1 to 10 Jupiter masses, are also found at these separations, though less frequently. But in the intermediate range, from roughly 13 to 80 Jupiter masses, the companion frequency drops dramatically. Brown dwarf companions at these separations are rare. The desert is real. Various explanations have been proposed for this pattern. The most widely discussed involves the different formation pathways for stars, brown dwarfs, and planets. Giant planets, in the current understanding of planet formation, grow through two main processes: core accretion, where solid material in a protoplanetary disk gradually builds up a rocky or icy core that eventually becomes massive enough to attract a gas envelope, and disk instability, where the disk itself becomes gravitationally unstable and fragments directly into a gas giant. Both of these processes operate within the disk and tend to produce objects in the planetary mass range. Stellar companions, on the other hand, form through the fragmentation of the molecular cloud core before or during the collapse, producing a binary system where both members have roughly comparable masses. This process naturally produces objects in the stellar mass range. Brown dwarfs in the close companion range seem to fall between these two processes, too massive to form readily through disk processes that favor planets, and too light to form efficiently through the cloud fragmentation that produces stellar binaries. They are, in a sense, caught in the gap between two formation mechanisms, and the result is that close brown dwarf companions are rare. But this explanation, while plausible, is not the whole story. The brown dwarf desert is not uniformly empty. Some brown dwarf companions do exist at close separations, and understanding why some systems have them while most do not is an active area of research. It is also important to note that the desert applies specifically to close separations, typically within a few astronomical units. At wider separations, brown dwarf companions are found at rates consistent with or even exceeding what is found for stellar companions. This distance dependence is a crucial clue to the formation physics. One important consideration is the effect of migration. Both giant planets and brown dwarf companions, if they form in the outer regions of a disk or cloud, can migrate inward over time due to gravitational interactions with the disk material. If brown dwarf companions form at wide separations and then migrate inward, the efficiency of that migration and the conditions under which it can happen might naturally produce the observed pattern of close separation depletion and wide separation enhancement. Alternatively, objects that do form at close separations might tend to merge with the star or be disrupted more often than objects at wide separations, further depleting the close companion population. The brown dwarf desert also has an interesting counterpart in the mass function of isolated brown dwarfs. When astronomers measure how many brown dwarfs exist as isolated objects at each mass, they find a distribution that is roughly continuous, with lower mass objects being somewhat more numerous than higher mass ones. This mass function does not show a desert. The depletion is specifically for close companions to Sun like stars, not for brown dwarfs in general. This suggests that the formation environment, specifically the presence of a nearby, more massive forming star, is what suppresses close brown dwarf companions rather than any intrinsic difficulty in forming brown dwarfs at a given mass. There is also growing evidence that the brown dwarf desert is not equally arid for all types of host stars. Stars more massive than the Sun, and stars that are metal-rich, may have a less severe brown dwarf desert, with brown dwarf companions appearing at higher rates than around Sun-like stars. This mass and metallicity dependence adds further complexity to the formation story and suggests that the physical conditions in the protostellar environment, the density of the cloud, the disk mass, the disk chemistry, all play roles in determining how mass gets distributed between the host star and its companions. What the brown dwarf desert ultimately teaches us is that the universe is not a uniform place. The formation of stellar and substellar objects does not proceed with equal efficiency at all masses and all separations. There are preferred outcomes, mass ranges and configurations that nature finds easy to produce, and there are disfavored ones, arrangements that the physics of formation resists. The desert is a map of that resistance, a region of parameter space where the competing formation processes each find the terrain unfavorable. In a broader sense, the brown dwarf desert is a reminder that absence can be as informative as presence. The fact that something is not where you expect it to be tells you something important about the processes that govern where things end up. A desert is a statement about climate, about precipitation, about temperature. The brown dwarf desert is a statement about star formation physics, about disk dynamics, about the mass function of fragmentation. Reading the absence is a skill as important as reading the presence. Astronomers who study the brown dwarf desert are, in a sense, detectives working from negative evidence. They are looking at a gap, a place where objects should be but are not, and asking what that gap reveals about the laws that govern the formation of worlds. The answer is still being assembled, piece by piece, as surveys find the rare exceptions that populate the desert and as theorists build more detailed models of cloud collapse and disk dynamics. The desert will eventually be mapped in detail, its edges defined, its rare inhabitants cataloged, its formation physics understood. And when it is, the brown dwarf desert will stand as one of those beautiful instances where a statistical anomaly, a curious gap in a distribution, led astronomy deeper into the fundamental processes of star and planet formation than direct detections alone ever could. For now, let the image of the desert rest in your mind, not as a place of emptiness, but as a place of meaning. A region defined by its quiet, by its absence of the expected, by the particular combination of circumstances that makes it inhospitable to a certain kind of formation. Every desert, physical or statistical, has its own specific reasons for being what it is. And every desert teaches something that the lush and populated regions cannot. When we think about moons in our solar system, the image that comes most readily to mind is probably one of rocky or icy bodies orbiting planets, illuminated by the distant light of the sun, receiving their warmth from that external source. The moons of Jupiter and Saturn are among the most scientifically interesting objects in the solar system precisely because some of them, particularly Europa around Jupiter and Enceladus around Saturn, receive enough tidal heating from their planet's gravitational flexing to maintain liquid water oceans beneath their icy surfaces. These subsurface oceans have made them prime candidates in the search for life beyond Earth, not because of sunlight, but because of internal heat. Brown dwarfs present an entirely different kind of potential host for moons. They are not illuminated by a distant star in the same way. They provide no visible light to potential moons orbiting them, at least not in any significant quantity. But they do provide something perhaps even more interesting: a continuous source of infrared heat, a warm glow emanating from their own interior, surrounding any orbiting moon in a low-level warmth that persists for an extraordinarily long time. The question of whether brown dwarfs can have moons is not merely speculative. Brown dwarfs form through the same disk-mediated process as stars, and protoplanetary disks form around brown dwarfs just as they do around stars. Evidence for protoplanetary disks around young brown dwarfs has been found in abundance. Infrared observations of young brown dwarfs in star-forming regions show the characteristic excess infrared emission that indicates the presence of warm dust in a disk. Millimeter wavelength observations have directly imaged disk material around brown dwarfs. The disks are smaller and less massive than those around Sun-like stars, which is expected given the lower mass of the central object. Objects that form in disks around brown dwarfs might more properly be called moons than planets, by analogy with the moons that form in the disks around giant planets in our own solar system. Jupiter's large moons, the Galilean moons, are thought to have formed in a disk of gas and dust that surrounded Jupiter during its formation, in a process similar to planetary formation around a star, but on a smaller scale. By the same logic, objects forming in the disk around a brown dwarf would be moon-sized to small planet-sized, orbiting their brown dwarf host rather than a star. The conditions for such moons depend strongly on the properties of the brown dwarf disk. Disks around brown dwarfs tend to be smaller in radius than disks around Sun-like stars, with the outer edge perhaps only a few tens of astronomical units from the brown dwarf rather than the hundreds of astronomical units that characterize some stellar disks. The temperature structure of the disk is determined primarily by the brown dwarf's own luminosity rather than by stellar irradiation from outside. In the inner disk, close to the warm brown dwarf, temperatures may be high enough to prevent ice formation. In the outer disk, temperatures drop to the point where water ice and other volatile compounds can condense. The distance from the brown dwarf at which water ice can survive in the disk, sometimes called the snow line or frost line, is closer to the brown dwarf than the corresponding distance in a stellar disk. This is because the brown dwarf is intrinsically less luminous, and so the temperature falls off more quickly with distance. The snow line in a brown dwarf disk might be only a fraction of an astronomical unit from the brown dwarf, meaning that icy materials can condense and accumulate much closer in than they would in a solar system. Moons forming outside this snow line in a brown dwarf system would be rich in water ice and other volatiles. They would accumulate material that in our solar system is found only in the outer regions, in the comets, and in the icy moons of the outer planets. A moon forming in a brown dwarf disk at what would be, relative to a solar system, a modest distance, could be a world rich in water, methane, ammonia, and carbon dioxide ices. Now consider what happens to such a moon once the disk has dissipated and the brown dwarf has settled into its long cooling phase. The moon orbits its brown dwarf host in the dark, receiving no sunlight, lit only by the faint infrared glow of the brown dwarf itself. At close orbital distances, the tidal forces exerted by the brown dwarf on the moon could generate significant internal heating, flexing the moon's interior in the same way that Jupiter flexes Io and Europa. This tidal heating, combined with the radiogenic heating from radioactive elements in the moon's rock and any heating from the brown dwarf's own infrared emission, could maintain liquid water beneath an icy surface for extended periods. The energy balance on such a moon would be quite different from any body in our solar system. There would be no sunlight to drive photosynthesis or to heat the surface directly, but there would be a gentle, persistent warmth from multiple sources: tidal flexing, radioactive decay, and the low but non-zero infrared irradiation from the brown dwarf. Whether this combination of heat sources would be sufficient to maintain the liquid water and chemical gradients that life requires is a fascinating question that astrobiologists have begun to take seriously. The habitability of moons around brown dwarfs would be a strange, alien kind of habitability. The surface of such a moon would be frozen, dark, lit only by the faint infrared glow of the brown dwarf and by whatever reflected infrared light came from the brown dwarf's own atmosphere. A brown dwarf in the T-dwarf temperature range would appear to a human eye, if one could somehow be placed at the surface of an orbiting moon, as a dim, dark red object, much larger than the sun appears from Earth if it were close enough, perhaps spanning several degrees of sky, but glowing only in wavelengths near the edge of visibility or entirely in the infrared. The night side of the moon, turned away from the brown dwarf, would be extraordinarily dark, darker than any naturally occurring night on Earth, with no solar illumination scattered by an atmosphere, no moonlight, no city lights. Only the faint background of distant stars and the very faint cosmic microwave background. A darkness so profound that the word night is almost inadequate for it. And yet beneath the surface, if the tidal and radiogenic heating were sufficient, the situation could be very different. A subsurface ocean, warmed from below by tidal flexing and from above by the geothermal gradient of a warm interior, could maintain liquid water indefinitely. The chemistry of such an ocean would be different from Earth's surface ocean, without the photochemical reactions driven by sunlight, likely dominated by geochemical processes at the water-rock interface. But geochemical processes alone, in the absence of sunlight, are thought to be sufficient to support life, as demonstrated by the deep-sea hydrothermal vent ecosystems on Earth, where chemosynthetic organisms live and thrive in the complete absence of sunlight. The question of whether life could exist on moons of brown dwarfs is genuinely open. The conditions are extreme in ways that we do not fully understand. The long-term stability of tidal heating depends on the orbital dynamics of the system. The chemistry of a permanently dark subsurface ocean is uncertain. The duration of the warm phase, relative to the timescales needed for life to emerge and evolve, is unknown. These are questions that current science cannot definitively answer, but the possibility is real enough to take seriously. And the taking of it seriously forces us to expand our intuitions about what habitable means. We evolved under a star. Our entire framework for thinking about habitability is colored by that fact. The warm yellow light of our sun, the cycling of day and night, the photosynthetically driven web of life that covers our planet, these are not universal requirements for life. They are the particular conditions of our particular evolutionary history. Brown dwarf moons remind us that warmth can come from many sources. That darkness does not necessarily mean lifelessness. That the patient, long-duration warmth of a slowly cooling substellar object might be a different but equally valid setting for the chemistry of existence. We do not know whether such moons host life. We barely know whether such moons exist in significant numbers. But the possibility is enough to change the way we think about where in the universe existence might take hold. The moons in the warmth of brown dwarfs are waiting to be found. Some of them may be orbiting in the darkness right now, a few light years away, warmed from below, cold on the surface, dark in every wavelength that human eyes can see, and perhaps not empty. Perhaps not empty at all. In the previous part, we imagined moons orbiting brown dwarfs and wondered about the warmth that might persist beneath their frozen surfaces. Tonight, let us go deeper into that idea. Let us descend, in imagination, through the ice and rock of a hypothetical moon orbiting a brown dwarf several light years from here, and think carefully about what we might find if we could somehow drill down through the cold exterior and reach the layers below. The concept of a hidden ocean, sealed beneath a thick shell of ice, is one that has become increasingly familiar in the context of our own solar system over the past few decades. The Voyager missions in the 1970s and 1980s gave us our first close looks at the moons of Jupiter and Saturn, and what they revealed surprised almost everyone. Io, the innermost large moon of Jupiter, was covered in active volcanoes, heated by the immense tidal forces of Jupiter's gravity. Europa, the next one out, showed a surface of cracked and refrozen ice that looked, to trained eyes, like the surface of a frozen ocean that was still mobile, still being resurfaced from below. The Galileo spacecraft in the 1990s confirmed what the Voyager images had suggested. Europa has a liquid water ocean beneath its ice shell, maintained by tidal heating from Jupiter. The ocean is thought to be roughly 100 kilometers deep, containing more liquid water than all of Earth's oceans combined, and it has been in contact with the rocky seafloor for potentially billions of years. On Earth, life began in or near the ocean, and the water-rock interface at the seafloor is one of the most biochemically active environments on the planet. By analogy, Europa's seafloor became one of the most exciting potential locations for extraterrestrial life in the solar system. Enceladus, a small moon of Saturn, provided an even more dramatic confirmation of the hidden ocean concept. The Cassini spacecraft, orbiting Saturn from 2004 to 2017, flew through enormous geysers of water vapor and ice particles erupting from the south polar region of Enceladus. Analysis of these plumes revealed not just water but organic molecules, molecular hydrogen, and silicon nanoparticles, the last of which are produced by hot water reacting with rock at temperatures above 90 degrees Celsius. The picture that emerged was of an active hydrothermal system at the seafloor of Enceladus's subsurface ocean, where hot water interacts with rock in conditions that on Earth support rich communities of chemosynthetic life. Titan, Saturn's largest moon, has a different kind of hidden liquid. Its surface, under a thick orange haze of organic chemistry, hosts lakes and seas of liquid methane and ethane. These are not water oceans, but hydrocarbon oceans, liquid in the extremely cold conditions of Titan's surface despite being at temperatures of around minus 170 degrees Celsius. Whether organic chemistry in liquid hydrocarbons could support life is deeply uncertain, but Titan's chemistry is so complex and so rich in organic molecules that it has made astrobiologists think carefully about non-water-based scenarios for chemistry and possibly for life. Now translate these concepts to the environment of a moon orbiting a brown dwarf. The scale and the details are different, but the fundamental physics applies. A rocky or icy moon orbiting at the right distance from a brown dwarf would experience tidal heating if its orbit is not perfectly circular. This tidal heating comes from the constant flexing and relaxation of the moon's interior as it moves slightly closer and further from the brown dwarf during each orbit, with the brown dwarf's gravity working slightly differently on the near and far sides of the moon. The magnitude of this tidal heating depends on the mass of the brown dwarf, the orbital distance of the moon, the eccentricity of the orbit, and the internal properties of the moon itself. For a moon at the right distance from a massive brown dwarf with a suitably eccentric orbit, the tidal heating could be comparable to or greater than the tidal heating experienced by Europa or Enceladus. The result could be a moon that maintains a liquid water ocean beneath its ice shell, powered not by sunlight, but by the gravitational interaction with its brown dwarf host. But brown dwarfs provide an additional source of warmth that is unique to them and has no analog in the moon systems of our solar system. The brown dwarf's own intrinsic luminosity, the infrared radiation from its slowly cooling interior, irradiates any nearby moon with a gentle but persistent heat. For a moon orbiting close to a brown dwarf, this irradiation could contribute meaningfully to the moon's energy budget, warming the surface slightly, potentially keeping the ice shell thinner than it would otherwise be. This infrared irradiation changes in character as the brown dwarf ages and cools. A young, warm brown dwarf in the L dwarf temperature range would irradiate its moons with substantially more heat than an old, cool T or Y dwarf. Over billions of years, as the brown dwarf cools, the irradiation decreases. Moons that were warmer in the early era of the system would gradually become cooler, their ice shells thickening, their subsurface oceans perhaps contracting or freezing from the top down. But the tidal heating, if the orbit is maintained, would be less sensitive to the age of the system. It would persist as long as the orbital eccentricity is maintained by gravitational interactions with other moons or with the brown dwarf's own slightly non-spherical gravitational field. There is also the heat from radioactive elements within the moon itself. Radioactive isotopes of elements like uranium, thorium, and potassium decay over time, releasing heat as they do so. This radiogenic heating is responsible for much of Earth's internal heat, and it was responsible for even more in the early solar system when short-lived radioactive isotopes were more abundant. A moon forming from rocky and icy material will incorporate some fraction of these radioactive elements and will be heated by their decay for billions of years. In the early life of such a moon, this radiogenic heating alone might be sufficient to maintain liquid water in the interior before tidal heating and brown dwarf irradiation become the dominant sources of warmth. The lifetime of a potentially habitable environment on a brown dwarf moon is one of the most fascinating aspects of this scenario. On Earth, the timeline from the formation of liquid oceans to the emergence of complex life involved billions of years. The total duration of Earth's potentially habitable phase, from the formation of stable oceans to the present, is about 4 billion years, and it will continue for several billion more. On a moon of a brown dwarf, the duration of the potentially habitable phase depends on how long the tidal heating persists, which depends on the stability of the orbital configuration, and this could in principle be very long, billions of years, possibly tens of billions. This duration aspect is one of the reasons that the brown dwarf moon scenario is taken seriously in astrobiology. Habitability requires not just the right conditions, but the right conditions for long enough. Life, as far as we know from our one example, takes a long time to emerge, a long time to evolve beyond simple microbes, and a very long time to develop the kind of complexity we see in the Earth's biosphere today. If moons around brown dwarfs can maintain habitable conditions for billions of years, the time argument for life does not immediately disqualify them. What would a subsurface ocean on a brown dwarf moon look like? Almost certainly dark, lit by no sunlight, perhaps dimly warm, near hydrothermal vents where hot water rises from the rocky seafloor. The water would be saline, enriched with whatever minerals dissolved from the surrounding rock over billions of years. The pressure at depth would be enormous, not as extreme as the deepest parts of Earth's ocean, but significant. And the chemical environment would be set by the interaction of liquid water with rock in the absence of any photochemical input from above. This last point is important for the question of life. Life on Earth is ultimately powered by two main energy sources: sunlight, captured by photosynthesis and woven into the biosphere through almost every food web, and chemical energy from the mantle of the Earth, released through volcanic and hydrothermal activity. In the deep sea, far from any sunlight, entire ecosystems run on chemical energy alone, on the oxidation of hydrogen sulfide and methane and hydrogen gas that emerge from hydrothermal vents. These chemosynthetic ecosystems are independent of sunlight and demonstrate that the requirements for life can be met without any stellar irradiation whatsoever. A subsurface ocean on a brown dwarf moon, supplied with chemical energy from hydrothermal activity at the seafloor, would be operating under conditions that in principle allow chemosynthesis. Whether that would lead to the emergence of life depends on factors that we do not understand well, even in the context of Earth's early ocean. The origin of life is one of the deepest unsolved problems in science. We do not know what the minimum requirements are beyond liquid water, chemical energy, and time. We do not know how probable life is given those ingredients, whether it is nearly inevitable or extraordinarily rare. The hidden oceans of brown dwarf moons remind us how much we still do not know. They are places that might exist in abundance in the galaxy, places that might have harbored chemistry for billions of years, places that might tell us something profound about the nature of life if we could ever find them and study them. They are also places we will almost certainly never visit, never sample, never directly observe in any meaningful way with technology we can imagine. They are, in the best sense, objects of pure imagination grounded in real physics. Real enough to study theoretically, too distant and too dark to observe directly. And in that combination of reality and inaccessibility, they hold a particular kind of appeal for a night like this. The goal is not to solve, but to wonder, not to arrive, but to drift. The hidden ocean waits in the dark beneath the ice of a moon that orbits a brown dwarf that none of us will ever see. And whether or not it contains life, whether or not anything has ever moved in its cold and lightless depths, it is there. Real, patient, dark, and utterly silent. Part of a universe that is far stranger and far more interesting than the bright surface of the sky we look at every night. There is something immediately relatable about weather. Of all the phenomena in the natural world, weather is perhaps the most intimate, the most immediate, the one most woven into the texture of daily experience. We wake in the morning, and the first thing many of us do, before we have fully formed a thought, is look toward the window to see what the sky is doing. Rain or sun, cloud or clear. The state of the atmosphere outside determines the clothes we wear, the plans we make, the mood that settles over the first hours of the day. Weather is the atmosphere in conversation with itself, and we are always listening to that conversation whether we mean to or not. It might seem strange, then, to talk about weather on a brown dwarf. A brown dwarf has no inhabitants to check the sky in the morning. It has no seasons driven by axial tilt, no warm ocean currents and cold land masses creating the pressure gradients that drive wind. Its atmosphere is not the thin, delicate envelope of a terrestrial planet, but a deep, crushing layer of gas that grades imperceptibly into the dense interior below. And yet, weather on a brown dwarf is real. It is vigorous, dramatic, and in some ways more extreme than anything the Earth's atmosphere can produce. The same fundamental physics that drives weather on Earth, temperature differences, pressure gradients, rotation, gravity, operates on brown dwarfs with far greater force and on far larger scales. The engine of weather on a brown dwarf is the outward flow of heat from the interior. As we have discussed, a brown dwarf is slowly releasing its stored thermal energy through its atmosphere and into space. This heat does not flow uniformly and smoothly outward. It percolates through the atmosphere in a complex, turbulent, three-dimensional flow, and the result is weather. Warm parcels of gas rise from deeper, hotter layers toward the cooler upper atmosphere. As they rise, they cool, become denser, and eventually sink back down. This convective overturning is the basic engine of atmospheric dynamics on brown dwarfs, just as convection in the troposphere is the basic engine of weather on Earth. But the scale and intensity of convection on a brown dwarf is vastly greater than on Earth. The temperature difference between the deep interior and the upper atmosphere can be thousands of degrees, far greater than the temperature contrasts that drive Earth's weather. The gravitational acceleration at the surface of a brown dwarf is many times greater than Earth's surface gravity, which affects how quickly material rises and falls. And the depth of the convecting layer, the atmospheric region where convection operates, is far greater than Earth's troposphere. On Earth, weather is largely confined to the lowest 15 kilometers of the atmosphere. On a brown dwarf, convection may operate through atmospheric layers hundreds of kilometers thick. The rotation of the brown dwarf is also a critical factor. Many brown dwarfs rotate rapidly, completing a full rotation in just a few hours. This rapid rotation creates strong Coriolis forces, the same effect that causes cyclones and anticyclones on Earth, that curves the paths of moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere. On a rapidly rotating brown dwarf, these Coriolis forces are so strong that they organize the atmospheric circulation into tight, parallel bands aligned with the equator, similar to the banded structure seen on Jupiter, but potentially even more pronounced. Jupiter's cloud bands, the alternating light zones and dark belts that make it one of the most visually striking objects in the solar system, are produced by this kind of rotationally organized circulation. Eastward flowing jet streams separate the bands from each other, and the interplay between these jets and the convective columns rising from below creates the complex, perpetually changing cloud patterns that Voyager, Galileo, Juno, and countless ground-based observers have documented over the decades. On a brown dwarf, Similar dynamics would operate, but with the additional complication of cloud chemistry that is far more exotic than Jupiter's ammonia ice clouds. The clouds themselves are weather systems. In the L dwarf temperature range, where silicate and iron clouds dominate, the formation and dispersal of these mineral clouds is driven by the same convective dynamics that drive the banding. Where convection is particularly vigorous, material is lofted higher into the atmosphere, where temperatures are cooler and silicate and iron vapors condense into cloud particles. Where the atmosphere is more stable and convection is weaker, the clouds thin out or clear entirely, creating the patchy structure that is responsible for the observed variability in L dwarf brightness. The turbulence within these cloud layers is itself extraordinary. Cloud particles of different sizes fall at different rates, creating complex microphysical interactions. Larger droplets of liquid iron or silicate rain downward through smaller particles, colliding with them, growing, or breaking apart. This is iron rain in the most literal sense. Liquid iron droplets falling through an atmosphere of compressed gas, driven by gravity, driven by the temperature gradient, forming and evaporating and reforming in a continuous cycle that has no analog in any weather system on any rocky planet we have studied. In the T dwarf range, where the silicate and iron clouds have sunk below the observable atmosphere and methane clouds have taken their place, the weather takes on a different character. Methane is a much lighter, more volatile compound than iron or silicate, and its cloud physics is more similar in some ways to the behavior of water vapor on Earth, though the temperatures and pressures involved are still far outside terrestrial experience. Methane clouds in T dwarf atmospheres may form and dissipate on timescales of hours to days, creating variability that can be tracked by monitoring the brown dwarf's infrared brightness over time. The variability of brown dwarfs has become one of the primary tools for studying their atmospheric dynamics. When a brown dwarf rotates and different parts of its atmosphere come into view, the changing cloud cover creates a varying infrared signal. By decomposing this signal, astronomers can infer something about the distribution of clouds, the location of clearings, and the length scales of the dominant weather patterns. Some brown dwarfs show simple, periodic variability that suggests a single dominant cloud feature, like a large clearing or a thick patch, rotating in and out of view. Others show more complex, multi-period variability that indicates multiple competing weather systems. The most detailed weather maps of brown dwarf atmospheres have come from Doppler imaging techniques applied to high-resolution spectroscopy. This method, adapted from the technique used to map star spots on stellar surfaces, uses the slight wavelength shifts of spectral features from different parts of the rotating brown dwarf to reconstruct a map of the atmospheric brightness distribution. The results have shown cloud structures that span large fractions of the brown dwarf's disk, enormous compared to anything in Earth's weather, but perhaps comparable to the largest features on Jupiter. Time-resolved spectroscopy has added another dimension. By taking spectra of a brown dwarf repeatedly over a full rotation period, astronomers can watch how the atmospheric structures evolve, not just spatially, but also in their spectral properties. This has revealed that the clouds on brown dwarfs are not static. They change shape, they move relative to each other, they grow and shrink. The variability is not perfectly periodic, but shows the kind of quasi-periodic behavior characteristic of real weather systems, systems that have a preferred timescale, but which are subject to chaotic fluctuations that prevent exact repetition. Theoretical models suggest that lightning on brown dwarfs could be extraordinarily energetic, with individual discharges releasing more energy than anything observed in our solar system. Some models suggest that this lightning could drive atmospheric chemistry, breaking apart stable molecules and enabling reactions that would not otherwise occur, producing complex organic chemistry in the deep atmospheres of cool T and Y dwarfs. This chemistry, if it occurs, would add yet another layer of complexity to the already extraordinary environments of brown dwarf atmospheres. Weather on a brown dwarf is, in the end, a kind of enormously scaled-up version of weather everywhere. The same physics applied to greater masses, greater temperatures, greater rotation rates, greater depths, produces greater phenomena. Iron rain instead of water rain. Silicate clouds instead of cumulus. Megastorms instead of hurricanes. Lightning that makes terrestrial thunderbolts look faint. All of it driven by the same patient, persistent outward flow of heat that defines the brown dwarf's entire existence. There is something almost comforting about that continuity. The weather on a brown dwarf and the weather outside your window tonight are governed by the same physical principles. Energy flows, temperature differences create pressure gradients, rotation organizes the flow, clouds form and dissipate. The scale is unimaginably different. The ingredients are alien. But the underlying logic is the same logic that decides whether tomorrow will bring sun or rain to wherever you are resting tonight. The universe uses the same rules everywhere. It just applies them to very different scales. And in that universality of physical law, even the alien storms of a brown dwarf feel, in some small way, familiar. We have spent time tonight thinking about the physics of brown dwarfs, their formation, their atmospheres, their strange clouds and alien weather, their potential moons and hidden oceans. All of that is fascinating on its own terms. But there is one aspect of brown dwarf existence that, for me, stands above the others in its power to reshape how we think about the universe. It is the question of time. Not time as we experience it in human life, not even time as measured in the rise and fall of civilizations, not even the geological time of Earth's history or the stellar time of our sun's life, but time on a scale that has no useful human analog, time measured in trillions of years, time so vast that every comparison falls short and every metaphor eventually breaks down. The current age of the universe is approximately 13.8 billion years. That number already resists easy comprehension. If you tried to count to 13.8 billion, one number per second, without sleeping or stopping, it would take you about 437 years. Every star you have ever seen, every galaxy that has ever been photographed, every cosmic event we have ever recorded has happened within this span of time. The Big Bang, the formation of the first stars and galaxies, the birth of our sun, the formation of Earth, the emergence of life, the rise and fall of every civilization in human history, all of it fits within 13.8 billion years. A brown dwarf of typical mass will take somewhere between 10 trillion and 100 trillion years to cool to the temperature of the cosmic background. Let us take the lower estimate, 10 trillion years, and sit with that number for a moment. 10 trillion is 10,000 billion. It is approximately 700 times the current age of the universe. If the universe's current age were represented by a single year on a calendar, 10 trillion years would be nearly 7 centuries. If you represented the current age of the universe as a single human lifetime of 80 years, then 10 trillion years would be about 56,000 years of human lifetimes stacked end to end. Every comparison I can make falls short, because our brains are not built to hold those kind of numbers. We evolved to track seasons and years and lifetimes, perhaps to think about history spanning centuries or millennia. Our intuitive sense of time runs out long before we reach billions, let alone trillions. What we can do instead is try to find the shape of the number, to understand it qualitatively even if we cannot feel it quantitatively. The shape of 10 trillion years, relative to the current age of the universe, is this: we are extraordinarily early. We live in what is, by the full timescale of the universe's future, the very first moments. The universe is 13.8 billion years old today. In 10 trillion years, that will seem like the opening breath of a speech that goes on for days. Almost everything that will ever happen in the universe, by sheer amount of time available, has not happened yet. We are at the very beginning of the long middle of the universe's life, before most of the interesting events in the universe's long, slow future have occurred. To understand why this matters for brown dwarfs, we need to think about the other objects in the universe and how long they last. The most massive, most luminous stars, the O and B-type giants that blaze at the top of the stellar sequence, burn through their fuel in just a few million years. Enormous and powerful as they are, their lives are brief by cosmic standards, candles that burn hot and fast and go out quickly. A star 10 times the mass of our Sun lives perhaps 30 million years. A star 30 times as massive lives perhaps 5 million years. These are the sprinters of the stellar world, burning bright and fading quickly. Our own Sun, a G-type star of middling mass, will live for about 10 billion years in total. It has already used about 4.5 billion of those years. When it has exhausted its core hydrogen, it will expand into a red giant, shedding its outer layers and leaving behind a hot, dense white dwarf, the compressed remnant of its core. That white dwarf will then cool slowly over billions of years, eventually fading to a cold, dark object sometimes called a black dwarf, though none yet exist because the universe has not been around long enough for any white dwarf to have cooled completely. The small red dwarf stars, the M dwarfs that are the most numerous true stars in the galaxy, are the long-lived champions of the stellar world. A red dwarf with half the mass of the Sun will live for perhaps 50 billion years. One with a third of the Sun's mass will live for over 100 billion years. The very smallest red dwarfs, those with about 8% of the Sun's mass, sitting just at the stellar threshold, will burn for trillions of years. These are the marathon runners of the stellar family, burning cool and slow and enormously patient by any human standard. But even the longest-lived red dwarfs will eventually exhaust their hydrogen fuel and fade. The universe will reach a point, somewhere in the range of 10 to 100 trillion years from now, when the last red dwarf has burned out, when the last of the main sequence stars has exhausted its fuel and left behind a cooling white dwarf. The era of star formation will have ended. The sky, if anyone were there to see it, would no longer be lit by fusion fires. At that point, the dominant luminous objects in the universe will be brown dwarfs. Not because they are bright, but because they will be the warmest things left. Everything else will be cooling remnants, white dwarfs slowly fading, neutron stars radiating away their heat, black holes slowly evaporating through Hawking radiation over incomprehensible timescales. And among all of these cooling objects, The brown dwarfs will still be radiating their formation heat, still faintly glowing in the mid-infrared, still patient, still enduring. The universe in this era, called the degenerate era by cosmologists, will be extraordinarily dark and cold by the standards of today. The cosmic microwave background, which today fills all of space with faint microwave radiation at a temperature of about 2.7 Kelvin above absolute zero, will have cooled further as the universe expands. The residual infrared glow of cooling brown dwarfs will be among the warmest signals in the universe. In a very real sense, the brown dwarfs will be the last embers, the last sources of significant warmth in a universe that is cooling toward its long cold equilibrium. There is something deeply affecting about this image. We live in a universe that is, at this moment, full of light and heat and activity. Stars forming, stars burning, galaxies colliding, nebulae glowing with the light of young stars, the cosmic microwave background filling all of space with the afterglow of the Big Bang. It is a universe in the full expression of its activity, energetic and complex and full of events. And we tend, perhaps naturally, to assume that this is simply what the universe is, that the universe is a lit and active place. But it is lit and active only in this early period. The long future of the universe is dark and quiet and cold. The fires will go out. The last stars will fade. The universe will enter the long, patient darkness of its middle and later ages. And in that darkness, the brown dwarfs will still be there, still emitting their faint warmth, still carrying within them the heat of their formation, patient beyond any concept we have words for. 10 trillion years, perhaps 100 trillion. The brown dwarf cools by imperceptible degrees, radiating photon by photon into an increasingly dark and cold universe. Around it, the galaxy it once belonged to has dispersed, its stars scattered by gravitational encounters over timescales of quadrillions of years. The Milky Way and Andromeda have long since merged and then dissolved. The bound clusters of matter that once defined galaxies have relaxed into diffuse halos of cooling stellar remnants. Everything is more spread out, more dilute, more separated. And still the brown dwarf glows, faintly, patiently, in the deep infrared of a universe that has grown very dark indeed. This timescale also recontextualizes the meaning of brown dwarfs today. They are not failed objects left over from the current era of star formation. They are the inheritors of the future. They are the objects that will be most relevant in the longest portion of the universe's life, the objects that will define the character of the universe for tens of trillions of years after the last true star has gone out. In that sense, calling them failed stars is not just wrong but backwards. The stars are the brief episode. The brown dwarfs are the enduring presence. Let that thought settle slowly into your mind as your breathing continues its quiet rhythm. We live in the brief, bright beginning of the universe's story, a time of fire and light that would give way, eventually and inevitably, to the long, patient dark. And in that long, patient dark, the brown dwarfs will endure. They will be there long after our sun is gone, long after every star visible tonight has faded, long after the concept of night and day has lost all meaning. Patient, quiet, warm at their cores, cooling by degrees too small to measure by any clock we can imagine. Still there, still glowing, still existing, in the only way brown dwarfs have ever known how to exist, quietly and for a very, very long time. cosmologists have developed a remarkable framework for thinking about the long-term future of the universe. It is a framework built from known physics, from the behavior of matter and energy as we understand them today, extrapolated forward over timescales that make the current age of the universe look like the blink of an eye. The picture that emerges is one of the most profound and most sobering in all of science. A universe that is cooling, darkening, and growing ever more diffuse, heading inevitably toward a state of maximum entropy, maximum disorder, maximum cold. This does not happen quickly. In fact, it happens so slowly that almost no human concept of slowness comes close to capturing it. But it does happen, and understanding the broad outlines of it helps us understand the role that brown dwarfs will play in the long future of the cosmos, and why they are in many ways the most important objects in that future story. The cosmological future is sometimes divided into eras, each defined by the dominant processes operating in the universe at that time. The era we live in now is called the stelliferous era, from the Latin word for star-bearing. It is the era of stars, the period during which fusion fires burn throughout the galaxies and illuminate the cosmos. This era began when the first stars formed, a few 100 million years after the Big Bang, and it will end when the last low-mass stars exhaust their fuel, somewhere in the range of 100 trillion years from now. Within the stelliferous era, we are early. Our universe at 13.8 billion years has perhaps another 85 trillion years of stellar burning ahead of it. The entire history of human civilization and of complex life on Earth represents less than 1/10,000th of the remaining stelliferous era. We are not near the end of the age of stars. We are near the beginning of its middle portion. As the stelliferous era progresses, the character of the universe changes. The massive, luminous stars that dominate the young universe burn out first, leaving behind neutron stars and black holes. The medium-mass stars like our Sun eventually exhaust their core hydrogen, swell into red giants, and then shed their outer layers to leave white dwarfs. The small red dwarfs burn on and on, outlasting everything else in the stellar census, becoming ever more dominant in the population of luminous objects as their larger cousins fade. And distributed among all of these, in numbers perhaps comparable to or exceeding the total number of true stars, the brown dwarfs drift, cooling slowly, their infrared glow fading but never quite extinguishing within the timescale of the stelliferous era. When the last red dwarf finally runs out of hydrogen, the stelliferous era ends and the degenerate era begins. This era is named for the degenerate matter that makes up its dominant objects. White dwarfs, the compressed remnants of stars like our Sun, are supported against gravitational collapse by electron degeneracy pressure, the same quantum mechanical effect that supports brown dwarfs against collapse. Neutron stars, the remnants of more massive stars that exploded as supernovae, are supported by neutron degeneracy pressure. And brown dwarfs are already in this category, already supported by electron degeneracy pressure, already members of the degenerate family. The degenerate era is expected to last from about 100 trillion years to approximately 10 to the 37th power years, a number so large that writing it out in full would require 37 zeros. During this era, the dominant luminous objects are the slowly cooling white dwarfs, which radiate their stored thermal energy over quadrillions of years. But among the white dwarfs, the brown dwarfs will also be present, cooler and dimmer, but still radiating, still part of the thermal fabric of the universe. During the degenerate era, The galaxies as we know them will no longer exist. The stars and stellar remnants that make up the Milky Way today are held in their galactic orbits by gravity, but gravitational interactions between objects over extremely long timescales will gradually disrupt those orbits. Some objects will be scattered outward, ejected from the galaxy entirely into the intergalactic void. Others will spiral inward, contributing their mass to the central black hole. Over timescales of perhaps 10 to the 22nd power years, the galaxy will have dissolved completely, its constituent objects scattered across a vast volume of space. Brown dwarfs, being relatively low mass and therefore somewhat more susceptible to gravitational scattering by more massive objects, may be among the objects ejected from the galaxy-scale structures first. They would then drift through the intergalactic void, cooling slowly, no longer part of any recognizable galactic structure, isolated in a universe that is itself growing more uniform and more dilute as expansion continues. The intergalactic brown dwarf, drifting alone in the dark of an era when galaxies have dissolved and stars have long since burned out, is perhaps the most poignant image in long-term cosmology. It carries within it the heat of a formation event that happened tens of trillions of years ago. Around it, the universe has changed beyond all recognition. The cosmic microwave background has cooled to microkelvin temperatures. The last white dwarfs are fading to black. The universe is approaching the end of even the degenerate era, and the brown dwarf drifts on, patient as ever, glowing in wavelengths so long and so faint that no instrument could detect them even if any instrument existed to try. Beyond the degenerate era lies the black hole era, when the dominant objects are the supermassive black holes that once anchored galaxies and the stellar mass black holes left behind by massive stars. Even these will eventually evaporate through Hawking radiation, a quantum mechanical process by which black holes slowly emit radiation and lose mass. A stellar mass black hole will take approximately 10 to the 67th power years to evaporate completely. A supermassive black hole takes even longer. These timescales make the brown dwarf's cooling time look brief by comparison. And eventually, after all the black holes have evaporated, the universe enters what is sometimes called the dark era. The last remnants of organized structure have dissipated. The universe is a nearly uniform sea of the lowest energy particles, photons of enormous wavelength, neutrinos, and the most stable fundamental particles. Temperature is essentially zero. Entropy is at its maximum. The universe has reached what physicists call heat death, the state of maximum disorder from which no organized structure can spontaneously arise. This trajectory, from the bright stelliferous era to the cold dark era, is the long arc of cosmic history as we currently understand it. It is a trajectory defined by the gradual dissipation of the energy deposited in the universe at the Big Bang, the slow conversion of organized, structured energy into disordered, diffuse heat. The stars are the most visible and most rapid part of this dissipation. But the brown dwarfs, cooling slowly over trillions of years, are the last significant emitters before the universe goes truly dark. Understanding this context changes how we think about brown dwarfs today. They are not peripheral objects. They are not interesting only as curiosities or as failed stars. They are the transition objects between the stellar era and the dark era. They are the bridge between the time of burning and the time of cold. They carry within them the last significant stores of organized thermal energy that will be released into the universe in any form that even loosely resembles radiation from a warm object. When we look at a brown dwarf through an infrared telescope today, we are looking at an object that will still be faintly glowing in the far future of the universe, long after every other source of light we can observe has gone dark. We are looking at something that is, in a very real sense, built to last. Not because it was designed with durability in mind, not because any intention went into its formation, but because the physics of its construction, the quantum mechanical foundation of its stability, the slow rate of its energy loss, all conspire to give it a longevity that nothing else in the current universe can match. The far future universe is a dark and cold place, but it will not be entirely lightless for a very long time. In the deep infrared, in wavelengths beyond the reach of any human sense, the brown dwarfs will still glow. Patient, enduring, the last warm things in a cooling cosmos. Still there, still themselves, still quietly existing in the only way they have ever known. There is a kind of comfort in that, if you let yourself feel it. The universe will grow dark, but it will not grow dark all at once, and not for an almost incomprehensibly long time. And in the long period before the last light fades, the brown dwarfs will be there, doing what they have always done, what they were made by physics to do. Glowing, cooling, enduring, patient beyond all measure in the quiet dark of a universe that is taking its time about growing cold. We have arrived at the philosophical heart of tonight's exploration. We have spent many hours now with the physics of brown dwarfs, with their formation and their atmospheres, their strange skies and their hidden oceans, their long cooling and their role in the far future of the universe. All of that science is real and important and beautiful in its own right. But beneath it, running through it like a quiet current, has been a philosophical question that we have been approaching from many directions without stating it directly. Tonight, let us state it. What does it mean to exist without brilliance? This is a question about brown dwarfs. But it is also a question about much more than brown dwarfs. It is a question about value and visibility, about the relationship between being noticed and being real, about whether significance is something that must be demonstrated loudly to be genuine. The brown dwarf raises this question simply by being what it is, a vast, complex, ancient, enduring object that spends its entire existence below the threshold of visibility, glowing in wavelengths that most instruments cannot detect, drifting through the galaxy without announcing itself, existing fully and completely without any of the drama that we typically associate with cosmic significance. Consider the stars. When we think about the universe, when we think about the grand story of cosmic history, the stars are the protagonists. They are the ones who matter in the conventional narrative. They synthesize the heavy elements that make up planets and people. They emit the light that drives photosynthesis and warms planetary surfaces. They provide the energy gradients that, on at least one planet we know of, drove the emergence of life. They are born dramatically in the collapse of gas clouds, visible as bright protostars embedded in glowing nebulae. They die dramatically in red giant expansions and supernova explosions that scatter newly synthesized elements across the galaxy. Stars are the story. The brown dwarfs are not the story. They are not the protagonists. They do not synthesize the heavy elements that life requires, because they never achieve the temperatures needed for the advanced nucleosynthesis that produces carbon and oxygen and iron. They do not emit visible light to warm planetary surfaces, at least not in any significant way. They do not die in explosions that enrich the interstellar medium. They form quietly, cool quietly, and in the very long run will simply fade to cold, without any of the dramatic endings that the stellar narrative is built around. And yet, brown dwarfs exist. They exist in enormous numbers, perhaps comparable to or exceeding the number of true stars in the galaxy. They exist for enormous spans of time, longer than any true star. They are complex objects with layered atmospheres, magnetic fields, internal dynamics, weather systems that rival those of the most dramatic planetary atmospheres we know. They form in the same way as stars, from the same material, through the same processes. They have everything that a star has except the one thing we have decided matters most: the sustained nuclear fire that makes them visible. If we judge existence by visibility, by the ability to be noticed, by the contribution of light to the broader environment, then brown dwarfs matter less than stars. They are the invisible members of the stellar community, present in abundance but unnoticed, contributing little to the luminous fabric of the galaxy. From the perspective of visibility, they are negligible. But visibility is a strange criterion for significance. It privileges the extrovert, the loud, the dramatic, the easily noticed. It values contribution to the ambient brightness over the quiet fact of existence itself. And when we look at the full picture of the universe, when we consider not just the current era of burning stars, but the full sweep of cosmic time, the privilege of visibility starts to look parochial. The stars burn bright and brief. The brown dwarfs endure. If we measure significance by duration rather than by brightness, the calculus changes entirely. There is a tendency in human thinking to conflate importance with visibility. We notice the loudest voices in a room, the most colorful clothes in a crowd, the brightest objects in the sky. Our attention is naturally drawn to contrast, to the things that stand out against the background. This is not a flaw in human cognition. It is a feature, a practical adaptation for navigating a complex world where not everything can receive equal attention. But when applied to questions of value and significance, it leads to systematic errors. We overlook the quiet, the dim, the consistent, the patient, the things that do not demand attention, precisely because they do not demand attention. The universe is full of things that do not demand attention. The dark matter that makes up the majority of the universe's mass does not interact with light at all, not even in the infrared. It exists, it has gravitational effects, it shapes the large-scale structure of the cosmos, but it is completely invisible to any form of electromagnetic observation. The neutrinos that stream through the universe in their trillions, passing through matter almost without interaction, are essentially invisible to us, and yet outnumber the protons and neutrons in the universe by a factor of billions. The void spaces between galaxy filaments, the cosmic voids that make up most of the volume of the observable universe, are not empty, but are filled with diffuse gas and dark matter that we are only beginning to probe. Brown dwarfs are perhaps the most relatable of these invisible things, the ones most amenable to the kind of philosophical reflection we are engaged in tonight, because unlike dark matter or cosmic voids, they are discrete objects with physical properties we can describe, atmospheres we can characterize, histories we can trace. They are things, in the way that stars and planets are things. But they are things that have chosen, in a manner of speaking, to exist quietly. Existence without brilliance is not a diminished form of existence. It is a different form, with its own character, its own requirements, its own particular relationship to time. Brilliant things, things that shine, are by nature expenditures of energy. To be brilliant is to be converting stored energy into radiation, to be giving yourself away to the surrounding medium. Stars shine because they are burning, because they are converting mass into energy through fusion, because they are spending the capital of their hydrogen fuel. And like all spending, this limits their lifespan. The brighter the star, the faster the spending, the shorter the life. Brown dwarfs, by not burning in the full stellar sense, by not shining in visible light, retain their energy longer. Their existence without brilliance is an existence defined by conservation rather than expenditure, by endurance rather than expression, by persistence rather than display. These are not lesser qualities. In many contexts, they are the more admirable ones. Think about the contexts in which we value quietness and endurance in human life. We admire the person who works steadily without seeking recognition. We respect the friendship that persists without drama through years of ordinary life. We value the teacher whose students only come to appreciate their influence decades later. We honor the caretaker who shows up every day without fanfare. In all of these cases, what we are admiring is a form of existence without brilliance, presence without display, contribution without visibility, endurance without acknowledgement. The brown dwarf enacts these values at a cosmic scale. It is present in enormous numbers throughout the galaxy. It contributes to the gravitational fabric of galactic structure, to the census of matter, to the faint thermal background of the infrared sky. It endures through timescales that dwarf every other category of object in the universe. And it does all of this without display, without visibility, without any of the brightness that would make it easy to notice and admire. There is something freeing about contemplating this. The universe does not require its most enduring members to be its most visible ones. The things that last longest are precisely the things that burn least brightly. The most patient are the most invisible, and the most invisible may also be the most numerous. If this is true of the cosmos, perhaps it is also true in smaller contexts. Perhaps the most patient, most enduring contributions to any system are the ones least easily noticed, the ones made quietly and consistently over long periods rather than dramatically and suddenly in moments of visible effort. Existence without brilliance is the brown dwarf's gift to cosmological philosophy. It asks us to reconsider what we mean by significance, to question whether noticeability is a reliable proxy for importance, to sit with the possibility that the quietest and most patient things in any system may be, in the longest view, the most essential. The brown dwarf does not need us to notice it to be real. It does not need our attention to endure. It was there before we had telescopes sensitive enough to find it, and it will be there long after the last of our instruments has gone dark and the last memory of human observation has dissolved into the deep time of a cooling universe. Its existence is not conditional on our awareness of it. It simply is, fully and completely and quietly, in the dark infrared spaces between the stars. Let that settle. Let the image of the brown dwarf, drifting in the dark, glowing faintly in wavelengths no eye can see, patient and enduring and utterly indifferent to recognition. Let that image become the last clear thought before the softer thoughts of near sleep begin to arrive. Existence without brilliance. not lesser, not failed, simply a different, quieter, more enduring way of being. If existence without brilliance is one half of the Brown Dwarfs' philosophical offering, then longevity without recognition is the other. And these two ideas are related in a way worth examining slowly, because together they form a complete picture of a kind of existence that the universe has made possible in abundance, in which we tend, systematically, to overlook. Recognition, in the human sense, is a kind of social light. To be recognized is to be seen, acknowledged, named, remembered. It is to have your existence registered by other minds, to leave a trace in memory or record or influence that persists beyond the moment. Humans are, among other things, recognition-seeking creatures. We want to be known. We want to matter to others. We want our presence to leave some mark on the world. And there is nothing wrong with this. It is part of what makes us social, what drives us to create and contribute and connect. But recognition is also, by its nature, temporary. It depends on the existence of those who recognize. When the last person who knew you is gone, your recognition fades to historical record, then to archive, then to silence. The most famous human beings in history, those whose names are known to billions, will eventually be forgotten as the species that carries their memory evolves or disappears. Recognition is as mortal as the minds that sustain it. Longevity, in contrast, does not depend on recognition. To exist for 1 trillion years is to exist for 1 trillion years, whether any other mind is aware of that existence or not. The brown dwarf drifting through the galaxy for trillions of years is not made more real by our knowledge of it, and it would not be made less real by our ignorance. Its longevity is a physical fact, independent of any observer, independent of any record, independent of any recognition. We discovered brown dwarfs in the 1990s. The first confirmed examples were found in 1995. But brown dwarfs did not begin to exist in 1995. They had been forming and drifting and cooling since the earliest epochs of galaxy formation, billions of years before any human eye looked upward at the night sky. The ones we observe today have been existing quietly and completely for their entire lives without our awareness. Some of them are older than our solar system. Some of them formed when the universe was only a few billion years old, when the Milky Way was still assembling itself from smaller proto-galactic building blocks. They were there, unknown, unrecognized, but fully present. This gap between existence and recognition is not unique to brown dwarfs. It characterizes most of the universe. The vast majority of stars were not individually known to any human for most of human history. The galaxies beyond the Milky Way were not recognized as galaxies until the 1920s. The cosmic microwave background, the oldest light in the universe, was not detected until 1965 and not recognized for what it was until careful analysis showed it to be the afterglow of the Big Bang. The dark matter that makes up most of the universe's mass is still not directly detected at all. Recognition is a thin layer applied to a vast reality that does not depend on it. But there is something particular about brown dwarfs in this context. Something that distinguishes their situation from the situation of unrecognized stars or undetected dark matter. The stars, once we built the tools to detect them, proved to be everywhere in the sky. They had always been there, obvious once we looked, requiring only the night and clear air to be seen. Dark matter is still unrecognized in the sense of not being directly detected. We know it must exist, but cannot point to it and say, "There it is." Brown dwarfs occupied a strange middle position. They were theoretically predicted to exist for decades before they were found. Astronomers in the 1960s and 1970s calculated that the mass function of star formation should extend below the hydrogen burning threshold and produce substellar objects in significant numbers. The objects were expected. They were predicted. And yet for decades, they could not be confirmed because the tools to find them were not yet available. They existed in both the mathematical prediction and the physical universe, recognized in theory but not in observation, present in the equations but not in the data. When the first confirmed brown dwarfs were found in 1995, astronomers who had worked on the theoretical predictions for 20 or 30 years finally had their confirmation. There is a poignant gap between the decades of theoretical work and the observational confirmation, a period during which the objects were known to some and unknown to the broader community and to all non-astronomers, during which they existed fully in the universe but only partially in human knowledge. Recognition came late for brown dwarfs. And even now, recognition is incomplete. The cool Y dwarfs that WISE and JWST have begun to detect, the coldest and most ancient of the brown dwarfs, are still being cataloged. The nearest ones have been found only in the past decade or two. Objects within a few light years of the solar system remained unknown into the 21st century simply because they were too cold to appear in the surveys that had been conducted. The census of the solar neighborhood, the inventory of objects within a modest radius of our sun, was dramatically incomplete until infrared surveys revealed the hidden population. Longevity without recognition means existing fully and completely while remaining outside the awareness of any observer. It means being old without having a history that anyone knows. It means having been through more time than the current age of the universe, in some cases, and having no record of that time, no narrative, no story that persists. The brown dwarf's trillions of years of future existence will also be, for the most part, unrecognized. Long before the brown dwarf has finished cooling, our species will be gone, our technology will be gone, the universe will have changed beyond any current recognition. The brown dwarf will cool and cool and cool into a universe that contains no observers to note its presence. This might sound bleak. A trillion-year existence that unfolds, beginning to end, in the absence of recognition. An endurance so vast that no memory could span it, no record could survive it, no story could tell it. From a human perspective, shaped by the recognition-seeking social instincts that define our species, this might seem like a kind of tragedy. All that existence, all that endurance, and for what? No one to see it. No one to remember it. No one to write it down. But this framing assumes that recognition is the measure of meaning. And the brown dwarf, by its very nature, challenges that assumption. The brown dwarf exists for a trillion years not because it seeks recognition, but because the physics of its construction makes trillion-year existence natural and inevitable. It is not striving for longevity. It is not enduring through effort. It is simply being what it is, following the laws that govern its structure, cooling at the rate those laws prescribe, existing in the configuration that its formation established. Longevity without recognition is not a consolation prize for objects too dim to be noticed. It is a straightforward consequence of physical law. The universe, if it has any preference, seems to favor it. The objects that last longest are precisely the ones that spend the least energy broadcasting their presence. The universe rewards conservation with duration. The quieter you are, in a sense, the longer you last. There is a lesson here, if we are willing to receive it, about the relationship between expression and endurance. The loudest, brightest, most visible things in the universe are also the most transient. The quiet, dim, patient things endure. This does not mean that brightness is bad or that quietness is better. Both are expressions of physical reality. Both are valid forms of existence. But it does mean that when we instinctively privilege the visible, the recognized, the acknowledged, we are privileging a form of existence that is, on cosmic timescales, brief. The brown dwarf will outlast every bright star in tonight's sky. It will outlast every galaxy we have photographed. It will outlast the era of stars entirely. It will be cooling in the degenerate era while the last white dwarfs fade to black around it. It will carry within it the heat of its formation for longer than human language has words for. And none of this, not one moment of it, depends on whether we know it is happening. Longevity without recognition. The brown dwarf teaches this not by saying it, but by being it, by existing patiently and fully, and for an incomprehensible duration in the dark infrared spaces between the stars, asking nothing of the universe but the permission to cool in peace. That, if you let it, is a remarkable thing to carry into sleep. The recognition you receive or do not receive tonight, this week, this year, measures nothing about the depth or duration of your existence. The universe is full of things that exist fully and completely without being noticed. Some of them have been doing so for billions of years. Some of them will continue doing so for trillions more. They are real. They are present. And their longevity is not diminished by the darkness that surrounds them. Science, at its best, is not just a collection of facts about the world. It is a way of changing how we see the world, of shifting the angle from which we approach familiar questions and revealing that the answers we assumed were complete were actually only partial. Every great scientific discovery does this to some degree. Every expansion of our instruments and our methods opens a window we did not know was there and shows us something that was always present but not yet visible. Brown dwarfs, as a scientific subject, have done this in several ways that extend beyond the purely astronomical. They have changed how we think about the stellar census, about the population of objects in the galaxy, and the incompleteness of any survey that relies on visible light alone. They have changed how we think about atmospheric physics, revealing that the chemistry and dynamics of planetary atmospheres apply at scales far beyond what we had previously considered. They have changed how we think about habitability, opening the question of whether warmth from non-stellar sources, from tidal heating and internal heat and infrared irradiation, might sustain the conditions for life in environments we would never have otherwise considered. But perhaps the most significant thing that brown dwarfs teach us, the thing that goes beyond the technical and into the more fundamental, is something about the nature of the quiet, about what resides in the parts of any system that are below the threshold of easy detection, about the reliable underestimation of the patient and the dim. For decades, astronomers built their understanding of the stellar population from the objects they could see. The bright stars, the ones that filled photographic plates and later digital detectors with their light, were the basis for theories of stellar structure and evolution, stellar populations, and galactic dynamics. The census seemed complete because the instruments were good and the surveys were thorough. But the census was not complete. It was missing billions of objects, perhaps half or more of all the discrete gravitationally bound objects in the galaxy, simply because those objects emitted most of their energy in a color that the surveys were not designed to see. This is a humbling reminder. The completeness of our knowledge at any given moment is partly a function of the tools available and the assumptions we make about where to look. We build theories on the data we have, and the data we have is always, in some sense, biased toward the things that are easiest to detect. The loud, the bright, the large, the dramatic are overrepresented in our observations relative to the quiet, the dim, the small, the patient. And so our theories inherit that bias. They are theories of the detectable, extrapolated to the undetectable, and the extrapolation is sometimes wrong in systematic ways. Brown dwarfs corrected this extrapolation. When infrared surveys began to find them in significant numbers, the picture of the galactic neighborhood changed. The solar neighborhood, within 30 light-years of the Sun, turned out to be substantially more populated than optical surveys had suggested. The nearest stellar neighbors included objects that had been completely invisible to previous surveys, objects so close that they would have been easy to study in detail had anyone known to look for them in the right wavelengths. The incompleteness of the previous picture was not a failure of effort or intelligence. It was a failure of instrument, a failure to ask the right question in the right way. The lesson generalizes. In any complex system, the quiet components, the ones that do not broadcast their presence in the most easily detectable signal, are systematically undercounted. Correcting for this requires deliberately extending our instruments into the difficult domains, asking whether what we see is all there is or whether there is a population of quiet things below our current detection threshold. Brown dwarfs also teach us something about the relationship between simplicity and complexity. From a distance, a brown dwarf might seem simple. It is a ball of gas that failed to become a star, slowly cooling in the dark. There is no fusion, no dramatically evolving structure, no death by supernova, none of the narrative landmarks that make stellar evolution feel like a story. It just cools. How complicated can that be? The answer, as we have seen, is extraordinarily complicated. The atmospheres of brown dwarfs are among the most complex environments in the observable universe in terms of their chemical and physical richness. The iron rain, the silicate clouds, the methane chemistry, the lightning, the banded circulation, the patchy variability, all of this emerges from what seems like a simple situation. A ball of gas, cooling slowly, with gravity and rotation. The complexity is not imposed from outside. It arises from within, from the interaction of physical laws that are themselves simple but which, applied to the right conditions, generate outcomes of extraordinary richness and variety. This is a deep principle of physics. Simple laws applied to complex initial conditions generate outcomes that are irreducibly complex and essentially unpredictable in their details. The weather on a brown dwarf cannot be calculated from first principles in any practical sense, even if we know all the relevant physical laws. The chemistry of a T-dwarf atmosphere is not derivable from the basic equations of quantum mechanics in any direct way, even though it is ultimately governed by them. The complexity is real, and it is a product of the simplicity of the underlying laws, not a violation of them. This means that whenever we dismiss something as simple, as too straightforward to be interesting, we should be cautious. The brown dwarf, that simple cooling ball of gas, turns out to have iron rain and billion-year storms and hidden oceans and a lifespan that outlasts every other object in the current universe. Simplicity at the level of description does not guarantee simplicity at the level of phenomena. The quiet things, examined closely, often reveal depths that the initial impression concealed. Brown dwarfs also teach us something about the timescales of knowledge. The theoretical prediction of substellar objects was made decades before the observational confirmation. Scientists worked with the mathematical certainty that these objects had to exist, building models of their properties and their spectra, making predictions about what surveys would eventually find, all without being able to directly confirm any of it. The knowledge was real, in some sense, during those decades of prediction, but it was incomplete, provisional, awaiting the confirmation that only observation could provide. The gap between prediction and confirmation is a regular feature of science, particularly at the frontiers where theory runs ahead of instrumentation. During that gap, the predicted things exist in a peculiar epistemic state, known in theory, unknown in observation, real in the universe, but not yet real in the verified record of science. Brown dwarfs occupied that state for 30 years. Dark matter occupies a similar state today, known with great confidence to exist, its effects measured throughout the observable universe, and yet not directly detected, not confirmed in terms of a specific particle or a specific signal. The patience required to work in that gap, to maintain confidence in a theoretical prediction through decades of failed searches and false alarms and instrument limitations, is itself a kind of intellectual endurance. The astronomers who believed in brown dwarfs through the 1970s, 1980s, and early 1990s were practicing something like the patience of the objects they were seeking. They were existing, intellectually, in a state of longevity without recognition, confident in something that the broader community had not yet confirmed, working toward a detection that they knew, by the logic of physics, had to come. When it did come, in 1995, the confirmation was not just a scientific result. It was a vindication of patience, of trust in the predictions of physical theory, of willingness to keep looking even when the looking was difficult. And the objects that were found, the brown dwarfs themselves, seemed almost appropriate as the subject of that patient search. They had been there all along, patient and unrecognized, waiting to be found by people who were themselves practicing a kind of patience. What we learn from the quiet, in the end, is that the quiet has things to teach. That the universe is not fully described by its loudest and most visible members. That complexity hides in simple seeming places. That the patient and enduring components of any system are systematically undervalued by approaches that privilege the detectable over the present. And that sometimes, finding what is really there requires building new instruments, asking new questions, and extending our attention into the domains where the interesting things have been quietly waiting all along. The brown dwarf has been waiting for a very long time. We are only just learning to see it properly. And what we are finding, as the infrared surveys and the space telescopes and the spectroscopic analyses accumulate, is that the quiet parts of the universe are far richer, far more complex, far more numerous, and far more enduring than the bright parts ever suggested. We have traveled a long way tonight. From the first introduction of brown dwarfs as the quiet, dim, patient inhabitants of the galaxy, through the physics of their formation and the threshold they approach but do not cross, through the brief deuterium flame and the long cooling that follows, through the alien chemistry of their atmospheres, and the strange beauty of their infrared glow, through the hidden oceans of their potential moons, and the philosophical questions their existence raises about brilliance and recognition and endurance. We have followed them into the far future of the universe, into the degenerate era, into the long dark that awaits when the last true stars have burned out. And we have asked what all of this means, what it tells us about the nature of existence and the relationship between visibility and value. Now it is time to rest. Not to conclude, not to summarize, not to tie everything together with a neat bow of meaning, but simply to rest, the way the brown dwarf itself rests, in a state of quiet existence that does not require anything else of it. The brown dwarf does not need to arrive anywhere. It does not need to finish. It is simply what it is, in this moment and in every moment for trillions of years, cooling slowly, glowing faintly, existing fully in the quiet dark. Take a breath now, a slow one, and let it out completely before the next one arrives. Notice how your body is heavier than it was when we began. Notice how the thoughts that felt pressing at the start of the night have softened, how they have been replaced by something larger and quieter, a sense of scale that makes the immediate feel less urgent. This is what it means to spend time thinking about the very large and the very long. Not escapism, not denial of the real concerns of a real life, but perspective, a recalibration of the proportions. The brown dwarf drifting a few light years from our solar system right now, one of the ones discovered by WISE or detected by JWST, is doing nothing dramatic tonight. It is doing nothing dramatic any night. Its atmosphere is churning with iron clouds and methane chemistry, and perhaps great storms that have persisted for longer than humanity has existed. Its core is warm with the heat of its formation, slowly releasing that warmth through the layers of its dense interior. Its infrared photons are traveling outward in every direction, some of them in the direction of Earth, some of those eventually entering the aperture of a telescope, some of those being recorded by a detector and turned into data that an astronomer will analyze. And the rest, the vast majority, simply traveling outward into space, undetected, unrecorded, real and present and unobserved. There is something deeply settling about this image. The brown dwarf exists whether or not any telescope is pointed at it. Its warmth radiates whether or not any detector records it. Its trillion-year existence unfolds regardless of whether any mind is aware of it. Existence does not require an audience. Warmth does not require a recipient. Duration does not require a witness. This night, wherever you are, whatever has filled your day, you are resting under a sky that is far more populated than it appears. The stars you can see, or would see if you looked, are the bright members of a much larger community. Around them, between them, in the dark spaces where your eyes find nothing, the brown dwarfs drift. Some of them have been drifting since before our sun existed. Some of them will still be drifting when the sun has spent its fuel and faded. They are there now, as they have always been, as they will always be for a time scale that the word always is barely adequate to describe. Think about the nearest ones. Lumen 16, the binary pair 6.5 light years away, discovered in 2013 despite being one of our closest neighbors. It had been there for billions of years without anyone knowing. It will be there for trillions of years more. Its two brown dwarfs orbit each other slowly, their atmospheres rolling with cloud patterns that shift with every rotation, their infrared light traveling outward in all directions, including toward a small planet where for a brief few decades in the 21st century, A few hundred astronomers paid attention to them and wrote papers about their atmospheric variability and their spectral types and their distance from the sun. And then those astronomers will be gone, and the brown dwarfs will still be there, orbiting each other, cooling, patient, and present in the dark. The universe is very old. It is also, as we have discussed, very young compared to what it will become. We live in the bright, early morning of a day that will last for trillions of years, a morning full of fire and light that will give way, gradually and inevitably, to the long, quiet afternoon and evening of the universe's life. And in that long, quiet period, the brown dwarfs will be the warmest things, the last embers in a cooling cosmos, patient and persistent in the way that only the things that never burn too bright can be. There is a kind of wisdom in that. Not a wisdom that anyone designed or intended. Not a lesson that the universe is trying to teach, but a pattern that emerges from the physics, a pattern that says something true about the relationship between expenditure and endurance, between brightness and duration, between the things that announce themselves and the things that simply persist. The bright things burn and pass. The quiet things remain. This is not a counsel to be dim or to hide or to refuse the natural expressions of energy and vitality that are part of being alive. The stars are magnificent precisely because they burn, precisely because their fusion fires illuminate the cosmos and synthesize the elements and heat the worlds that orbit them. There is nothing wrong with burning brightly. There is nothing wrong with brilliance. But there is also nothing wrong with the other way, the cooler, quieter, longer way. The way of the brown dwarf. Some nights are for the stars, for the bright points of light that have captured human attention and imagination for as long as we have been looking up. And some nights, like this one, are for the spaces between the stars. For the faint infrared warmth that drifts through the galaxy unnoticed. For the objects that exist without demanding recognition, that endure without needing witness, that cool slowly toward a future so distant it cannot be imagined from where we stand. Tonight was for the brown dwarfs, for the failed stars that are not failed, for the quiet members of the galactic community that have been here all along, waiting to be found by instruments sensitive enough to detect their faint warmth. For the threshold objects, neither star nor planet, that occupy the in-between space with a completeness and a patience that neither category can match. They are out there right now, in the dark between the visible stars, warm at their cores, cooling at their surfaces, rolling with alien weather in their atmospheres, perhaps hosting moons with hidden oceans, drifting in their slow orbits through the Milky Way. Some of them alone, some of them in pairs, all of them patient, all of them glowing in the infrared, in the cold light that I was built to see. And you are here, wherever here is for you tonight, resting in your own kind of warmth, your own body generating its own faint heat, your own mind cooling slowly from the activity of the day toward the quiet of sleep. There is a kinship in that, if you want to feel it. Not a literal kinship, not a biological one, not one that requires anything of you. Just the kinship of being a warm thing in a cold universe, of existing for a duration that feels long from the inside and brief from the outside, of carrying heat that was given to you by processes you did not choose, and that you will release, slowly, over the course of a life that is brief on cosmic scales and entire on human ones. The brown dwarf does not know that it is cooling. It does not experience its trillion-year existence. It does not carry the knowledge of its own patience or the awareness of its own endurance. It simply exists, fully and completely, In each moment, following the laws that govern its structure, releasing its warmth at the rate those laws prescribe. You, on the other hand, can know. You can hold in your mind the image of the cool infrared light drifting through the dark spaces of the galaxy, the patient brown dwarfs outlasting the stars, the hidden warmth of objects that were invisible until we learned to look in the right colors. You can let that image settle into the deeper layers of awareness, below the day's concerns, below the week's plans, below even the slow, deliberate thoughts of near sleep begin to arrive. You can let it rest there, as a reminder of scale, as a companion for the quiet, as a presence in the dark that asks nothing of you, but perhaps offers something. Not brilliance, not drama, not the roaring fusion fire of a star that announces itself across the galaxy. Just warmth, just patience, just the quiet, persistent, infrared glow of something that has always been there, that will be there long after tonight is over, long after this year is over, long after this century and this millennium and every era that human memory can span. The cold light is real. It is out there right now. And for a little while tonight, on the long journey towards sleep, we found it together. Rest now. The brown dwarfs will be there when you wake. They will be there for a very long time after that. Patient, quiet, warm in the dark, existing without brilliance, enduring without recognition, cooling slowly toward a future that no mind alive today will ever see. Good night.